Yeah, welcome back from a lunch break. Now we have a talk from Elina Fuchs. Sorry, Wolf Fuchs. It's a similar. Yeah, sorry. About quantum sensing, and she's a junior professor at the University of Hannover. And yeah, I think you can say best of yourself, what you're doing there, and a warm applause for Elina. And yeah.
Thank you very, very much for the invitation to come to this European Summer School. I think it's a great format, and I'm very happy to be here, and I hope I will hear many questions from you. Yeah, my name is Elina Fuchs, and I work in particle physics phenomenology. So I'm a theoretical physicist, and I'm interested in finding out what additional particles there can be that we haven't found yet that could solve the big questions that the standard model leaves to us. And I am a junior professor at the Leibniz University of Hannover, together with the National Metrology Institute of Germany. That's the Physikalisch-Technische Bundesanstalt in Braunschweig. So that's what PTB stands for. And my work is included in our Excellence Cluster Quantum Frontiers and our collaborative research center DQMAT. So there are many quantum initiatives that make this work very fruitful and embedded into research of neighboring disciplines. And I'm very happy that hopefully this year, finally, I will also start a new joint position with DESI and the University of Hannover. So I thought, because this is, I guess, quite interdisciplinary also with your different backgrounds from physics, engineering, quantum physics, quantum engineering, and so on, I thought I'd start by telling you where I learned physics and where I have done my research so far. And if you want to chat about the different programs or opportunities of moving abroad and doing the next step in the research career, I will be very happy to chat. So I'm from the north of Germany, from Hannover. And I studied in Göttingen, that's very close by, approximately here. I did my bachelor and my master, but during this time I also always used every opportunity I could find to go abroad and participate in international student programs, such as Erasmus in Helsinki. And I also spent one summer at DESI already as a student to do a summer research internship. And in the summer afterwards, I went to Fermilab near Chicago and also to CERN, the European Particle Physics Research Laboratory in Geneva, to do more research experiences, both in theoretical and in experimental particle physics. And those experiences were so motivating for me that I returned to all of these places of my summer internships, and they really convinced me I wanted to continue in particle physics. So I can only warmly recommend you, if you still have time before you graduate as a master student, to look out for such summer student programs. Also the Institute for Heavy Ions in Darmstadt and some Max Planck institutes offer such summer student programs. If you want to hear more, I can tell you more in the coffee break. And then, I liked DESI so much that I moved there for my PhD. Actually, I already did my master's thesis there, and then I stayed. And after these 3 years of the PhD, I thought it was time to move even further away. And I had never been to Israel before, but then I moved there for 4 years. So initially it was planned for 3 years, but then I stayed for 4. And that was a very inspiring time of working in a new area where I hadn't been before geographically, but also I learned a new approach to particle physics, less from doing precision calculations, but more about thinking about new models and new opportunities, also how to look for new physics. Until my PhD, I had mostly worked on particle physics at Colliders, and here it was at the Weizmann Institute of Science in Rehovot, where I started working also on the interface of atomic and particle physics to try to learn if there could be very light new particles. This is also something I will tell you about today. And then I moved on to Fermilab and the University of Chicago, so it's not south of it, but of course you know where it is. And that was also a place where I had already done a summer internship, so it was very nice to come back. Unfortunately, this was also the time of the pandemic, so I had less opportunities to really explore the region. Nevertheless, the physics and the mentors I had there were very inspiring. And then in 2021, it was time to move back to Europe. I was very happy to come back to Europe and to work at CERN, the European Center for Particle Physics Research. And there I also became the theory coordinator of the CERN Quantum Technology Initiative, which is still quite young. And it was a very exciting time to push forward the proposal to move to a second phase of the quantum initiative. And now in these days, quantum initiatives are growing across the world. At the same time, I started a junior professorship in my hometown in Hannover, but I was still living in Geneva. But then last summer, I also finally moved back to Germany. All these positions were still limited time contracts, and the search continued to find a permanent position. And last year, luckily, I got the good news that I won a program from the Helmholtz Association that runs 18 research laboratories in Germany, including DESI here in Hamburg, for a joint appointment program to have a permanent position and a professorship at a research laboratory and a university. So this worked out with DESI and the University of Hannover. So I look forward to starting this, hopefully in September. And yeah, so what do I want to tell you about in these lectures? So I'm assuming you have a little bit different, you have different backgrounds. So please, if I go too slowly and you know everything of this already and you get bored, tell me. And on the other hand, if I say some things or show only a few times, on very few slides, I show some equations and you think that looks completely bizarre to you, please also let me know. And then we will take the time to discuss them in more detail. But let's start with a big picture. So as particle physicists and cosmologists, we really want to do research about the fundamental elementary structures of the universe, connecting to so old questions that already ancient Greek philosophers asked about. So what the universe is made of and what holds these constituents together. And we want to find out how we can observe objects that are invisible to our senses. And we want to find out how we can model what happened to the particles in the early universe and how we can test these hypotheses. And for this, to study what happened at very high energies that were present in the universe at early times, shortly after the Big Bang, we need to reach very high energy because that corresponds to the temperature that was still very hot in the early universe. Or we need to have a very good resolution of uncertainties to understand small deviations and learn from the measurements today about what happened in the time before even atoms and galaxies formed. And answering one question always brings us to the next level of understanding. So let's zoom again into the building blocks of the universe. So you all know that crystals are not the elementary building blocks. They consist of molecules, they consist of atoms. If you look further, you find the nucleus, but the nucleus is not elementary. They are the quarks, these circles inside, and they are held together by a force. That's the strong force. We will look at all these forces. And the force carriers of the strong interaction are the so-called gluons, shown here as these spirals. So quarks and electrons are already elementary particles, but they are not all. And as I said, if we want to study further, they go back in the time of the universe, we need higher and higher resolution or higher energy. And so to understand what happened early in the universe, it helps to understand very well what happens to elementary particles. Let's monitor a little bit where we are standing now before we do a survey of the particles that we know so far and the questions that they can answer and the questions that they cannot answer. So typically, when we look towards the unknown physics, to look for something that we don't know yet, we move in a two-dimensional plane. Sometimes there are even more parameters, but these usually appear. If we build a new model of adding new parameters and new particles, we're interested what mass a particle has and how strongly it interacts. And if the particle is not too heavy, so if we can produce it with the energies we have so far, and if it interacts relatively strongly, then it's relatively easy to find it. So if we don't, so we have found particles, and if we predict new particles of relatively sizable interaction strength, and we do the experiment where the experiment should be able to find something and we don't find anything, then we can say, okay, this assumption does not hold there. So this particle at least does not have such a mass and such an interaction. So we can exclude the upper left triangle. And then if we want to move towards the unknown territory, for example, to find particles who have a much weaker interaction, we need more precision, or we have to repeat an experiment more often to even find rare events. So these are two possibilities to move forward in this unknown direction. Or if we want to find heavier particles, we might need to increase the energy in our experiments such that we can produce these heavy particles if the energy wasn't sufficient so far. It can also help to increase the precision. So precision is useful in two directions. Because with high precision, even at lower energies, we can indirectly become sensitive to effects of heavier particles that would affect our observables, our measurements at the energies reachable so far. So we will several times see such diagrams of mass and interaction, even if they will be different interactions. Okay, so before we go into details, a rough overview how we typically test particle physics hypotheses today. The classical possibility, and you've certainly heard about it, are big colliders that collide beams of particles such as electrons and positrons, or protons and antiprotons, or protons and smash them at super high energies and look for the decay products of new particles that are created. Often these particles that are created are not stable, so we cannot directly find the new particles in the detectors, but they decay further and we detect the decay products and reconstruct the object, try to reconstruct the object that was created in the meantime. So that's the energy frontier, reaching up to 13.6 tera-electron volts today at the Large Hadron Collider at CERN, and future colliders are in the planning. If we speak about precision observables at colliders, we already call it precision if it's at the percent level. Some things have been measured even down to 10 to minus 5, but only few parameters. Another possibility to learn about the early universe is to directly observe messengers from the universe. So for example, photons, but photons only look back up to this cosmic micro, so the photons from the cosmic microwave background only look back to this slice in the time of the universe. But if we manage to detect gravitational waves, they could propagate from even earlier times in the universe and tell us about even more fundamental processes. And there one can detect objects of very high energies. Another possibility is, as I said, to repeat rare processes that happen so rarely that it's really hard to detect them, or if we detect them, they have a large statistical uncertainty. If we repeat them many times, we have a chance to measure them better. So they are high-intensity experiments, for example, to hit a beam of particles on a target and things decay. And the topic I want to talk about here today are precision measurements using, in particular, quantum sensors. And there we make use of the phenomenal precision that are already reached in frequency measurements in atomic clocks. Yes?
So like on the cosmic messengers, why is the energy negative? Like we got, for example, for quantum sensors like electron volt, but like here we got minus.
Oh, no, it's a range. It's like from giga electron volts to 10 to the 8 tera electron volts. Maybe the notation was misleading. Are there more questions about the range of applicability? Yes, please.
Why is the wave of the photon only coming back to the specific point in time?
That's because the photons would not propagate freely before. If there were ions and free-floating electrons, they would be scattered from there or absorbed. And from this, this is the cosmic microwave background, the last time slice of the scattering of the photons. And from there, they can propagate freely until we detect them today. So that's a beautiful chance to really measure the photons. And this cosmic microwave background means They are measured in a power spectrum, so at which wavelengths and under which angles we observe them to reconstruct the whole sky. Thanks for the questions. Okay. More questions? Then we continue for now. In the first part, I will speak about where we are standing with particle physics today and what possible signals from models beyond the standard model we expect to find. Of course, we can look for anything, and if we find something, it will be exciting, but I will also put some emphasis on two well-motivated signals that we are for sure interested in. And in the second part, we will discuss how to test physics beyond the standard model with quantum sensors. Before we continue, let me ask you about your backgrounds. Who is studying physics in the master? All, okay. So, and who is doing a master with an emphasis on quantum technologies? Also almost all, okay, or some. Okay, who has studied at least an introductory lecture to particle physics? Okay, even more than I thought. So maybe some things will be a bit a repetition for you, so you can tell me if you want to hear more advanced things. And who has already done some physics beyond the standard model? Only a few. Okay, good. So that will be new for most. Let's start. So I already almost answered your question in my introductory slides, but which elementary particles, I mentioned a few, but not all. Which elementary particles do you know already? Yes? The Higgs, yes. Mm-hmm. That's the one that was discovered last. Yes? Yes, exactly. So they are matter particles that we take as constituents to build the matter. But yes, what else? Neutrinos? Yes, they are also fermions, so we also count them as matter particles. But they are very elusive. They interact very weakly, and they are considered to be massless in the standard model, but they were found to have a mass. Yes, and what else? Yes, and they hold the particles together. They are the force carriers. Good. So from the very elementary level, you already know electrons and photons, and if you know more, you will learn what the nucleus consists of. And you have already learned that for the particles, we also have antiparticles as their charge conjugates. For the electron, that's the positron. And there is a hypothesis for neutrinos that they might be their own antiparticles, but this is an open question. Okay, so let's briefly review the building blocks of the standard model. Atoms are mostly made of the first generation of the fermions. We have 3 generations. The first consists of the up and down quarks and the electron. And up and down quarks are the main constituents of the protons and neutrons. Then you already mentioned the neutrino. They are leptons, so they don't interact strongly. They just interact via the weak interaction, and they are considered massless in the standard model. And we have copies of these, also the second generation and the third generation with increasing mass. And again, the quarks appear in these doublets. The leptons also appear in doublets, so they belong together and arranged under a certain symmetry group. We will come to symmetries. And these are the matter particles. It's the building blocks. We have found the fermions. Okay, you already mentioned gauge bosons. So what do we mean by gauge? So that means, as physicists, we're always interested in symmetries because they simplify our description of nature. They also help us to formulate an elegant description, and they also exclude terms in a Lagrangian that describes the interactions by finding out which terms are not invariant under symmetry. So in the we wonder which Lagrangian, so in some cases one uses a Hamiltonian. In particle physics, we typically use Lagrangians. We ask which Lagrangian is invariant under a certain symmetry transformation. And the symmetries are described by symmetry groups. They are described by their generators. And in most cases, there are different symmetries. There are discrete symmetries, like a flip of the sign of, for example, how something transforms under a parity flip, a flip of space-time, how something transforms under a flip of the charge. There are also discrete symmetries by allowing only, for example, even terms of a field, no odd terms. If the field flips to minus its field under this parity. And most symmetries we're interested in are continuous symmetries, so that means we have one parameter like this alpha of x that can take continuous values, and we're especially interested in so-called Lie groups that have good symmetry properties and found the basis of the description of interactions. And if we speak about gauge bosons, we refer to gauge symmetries. That means we demand invariance under local transformations such that these transformation parameters can depend on the space-time coordinate x, where we work in a 4-dimensional quantum field theory of 3 space dimensions and 1 time dimension. Are you familiar with this, or yes, good. And here's one example of the simplest symmetry group of just one free parameter. That's a U1 group, and that's the basis of formulating electromagnetism and having a theory, having a Lagrangian that is invariant under such transformations of a fermion field transformed to this transformed field guarantees us the conservation of the electric charge, but only if we introduce a new boson, a so-called gauge boson. To tell the full story, the symmetry group of the standard model is a product group of the SU3. That's the group describing strong interactions, and the conserved charge is called color. And the gauge bosons that we need to introduce are the 8 gluons. Why 8? Do you know why there are 8 gluons? Yes, there are 8 generators, because this is an SU3 group, and any SUN group has n² minus 1 generators. So that's why we expect 8 gauge bosons, and they are the 8 gluons. They are copies of each other, but they have different combinations of their color. They live in the adjoint representation of this group. Then, and this group is conserved, it's not broken. Then the next part is the electroweak symmetry. So that's a product of SU2 transformations that only act on left-handed fermions, on left-handed particles. So they form a doublet under SU2, and the ladder operators of this group, they transform the lower into the upper component. And we have a U1 symmetry, but that's not the U1 of electromagnetism, it's the U1 of the hypercharge. And the unification of these two groups can then be described by 4 generators. There are 3 generators of the SU2 and 1 of this. But this group is not conserved, it's broken down to a subgroup. That's the one that actually gives rise to the electromagnetism we observe. And the breaking of the symmetry, that means we break 3 generators, gives masses to 3 gauge bosons, namely the W plus and W minus boson and the Z boson, these ones here. But the photon remains massless as a consequence of the conserved U1 subgroup. And a very interesting consequence of the symmetry breaking is that we predict a physical degree of freedom, the Higgs boson, in order to conserve the degrees of freedom. Okay. Yes?
Like breaking the symmetry would imply like not conserving a physical quantity, or like?
Mm-hmm. Breaking the symmetry means that the Lagrangian is no longer invariant under transformations of one generator of that group. So there can be several generators. Some transformations under some might be preserved, and under some others broken. And broken means that if you express the Lagrangian in terms of the transformed fields, it is not the same as the Lagrangian of the original fields anymore.
Okay, and in terms of like stuff that could happen in our laboratory, like what would a symmetry breaking imply?
So the symmetry breaking has very interesting consequences, because we need to preserve the degrees of freedom from before the symmetry breaking and after the symmetry breaking. And here Yeah, and one consequence can be that we predict the existence of a physical particle that we can look for in the laboratory. Or was your question, what happens if a symmetry is not preserved, so if the Lagrangian changes? Then we would say it's unphysical, because if we require a symmetry, the observables have to be invariant under this. The fields can change, but the final Lagrangian must be invariant. But the symmetry breaking has to be there. There has to be clarified which part of the symmetry is broken. We come to a few more explicit cases, but maybe come back to this if it's not clear afterwards, okay? Yeah, so we can count here that in this SU2 group there are 3 generators. That means there are 3 massless gauge bosons that we have to introduce in order to preserve the symmetry, because just transforming the fermions doesn't make the theory invariant. We also have to introduce gauge bosons to make it invariant. But the gauge bosons need to be massless, otherwise the mass terms break the symmetry. So what we expect from this are 3 generators, so n squared, so 2 squared minus 1 is 3. We expect 3 associated massless gauge bosons of spin 1. Spin 1 particles without a mass have 2 degrees of freedom. So these would be 6 degrees of freedom. Here's 1. And then we break the symmetry, and here we had so the idea is to have we come to this on the level of the Lagrangian, a scalar potential of a complex scalar, and that has 4 degrees of freedom, and 3 of these degrees of freedom result in the prediction of new massless particles, but because it's not a global but a local symmetry, they are eaten by these gauge bosons and are not visible, but the 4th one is actually the physical Higgs boson that we expect. So maybe now I said already something I wanted to explain more at the level of the Lagrangian. Yes, please?
Does the Higgs boson have mass?
Yes, it has, and we come to it why. It gives mass to itself by the mechanism of spontaneous symmetry breaking. I will explain it on the next 2 or 3 slides.
Does it have anything to do with the generators? Because the 3 generators retain mass, but the Higgs boson is 1.
Yeah, the Higgs boson is not the Higgs boson doesn't come from it. So the Higgs boson is not a gauge boson. It is not introduced because of a generator, but it is introduced because we impose a potential. And now here's no blackboard. Let me maybe explain this slide and the next, and then I come back to your question about the role of the Higgs boson and how we count it. So, so the standard model is a really rich theory and very elegant. So it's a theory that it describes many phenomena to an amazing precision. And if we write it in an elegant way, it fits onto a coffee mug. And what we see here are the different terms that describe interactions of the gauge bosons, the fermions, and the scalar, the Higgs boson. Let's illuminate this a little bit. So here this term, these F mu nu, they are the field strength tensors of the gauge bosons. And this implies the sum over all. So the 8 gluons, the 3 bosons of the 4 bosons of the electroweak theory, the W plus, W minus, the Z, and the photon, they are summarized here. So that tells us how the gauge bosons self-interact. The photons don't couple to each other because they are neutral, electrically neutral, but the other bosons, which come from non-abelian symmetries, they have self-interactions. The second term describes how the fermions have a kinetic term, so that's from this derivative, but this is a so-called covariant derivative that also contains the gauge bosons, so it tells us how fermions interact with gauge bosons. The third term already includes the scalar, that's the Higgs boson, that somebody mentioned as the first elementary particle that came to your mind. Very nice. So that's this phi is the scalar field, and here it is described how it couples to a pair of fermions, and the coupling strength is given by the Yukawa interaction. And then the scalar appears at more places, namely in this kinetic term that describes the derivatives of the scalar field. So these derivatives are needed to make it a dynamical field such that it has equations of motion, non-trivial equations of motion. But this capital D also includes the gauge bosons, so it also tells us how a Higgs boson can couple to W plus W minus bosons, to Z bosons, and only indirectly to the photons or gluons. And then we come to this part. This is the potential of the Higgs. Here's left unspecified, but the standard model has the minimal case of introducing Higgs potential. That's where we have just one scalar, that makes it already minimal, and where we include terms up to 4 powers of the Higgs field, so that the theory remains renormalizable, and we have a Lagrangian of mass dimension 4. So this we can see here in pictures. Maybe we start with the Higgs potential because you were wondering about this. We can write down the potential of the Higgs boson, and that then, if we spell it out, if we multiply all terms, we find that there can be a quartic interaction of 4 Higgs fields interacting in one vertex of 3, and after the symmetry breaking, the Higgs also gets a mass. And these are these other interactions: a scalar interacting with a pair of fermions, the scalar, which is the Higgs, interacting with a pair of gauge bosons, a photon interacting with a pair of electrons, and here the self-interactions of gauge bosons. Okay, but how do the particles that we observe to be massive, how do they get a mass? So I already said this. If we write down explicit mass terms of the gauge bosons, that breaks the symmetry that we introduced, that make the Lagrangian so elegant. On the other hand, experimentally, we observe that the gauge bosons have masses, so we need to find a solution how they get masses. And that's the mechanism of spontaneous symmetry breaking. To explain what spontaneous means in a contrast to explicit, let us imagine a rod, like a branch or like a stick, as one sometimes has to point at the slides. So if we put it in a line to the z-axis, it has a symmetry of rotations around its own axis. And we can rotate around any angle the stick maps to itself. However, if we push against it with an external force that is not parallel to the symmetry axis, then after applying more and more force at a certain point, this rod will bend. And the symmetry is broken explicitly by this external force. So there we see, if we rotate it around the z-axis, it's no longer symmetric. What happens, however, if we apply pressure, if we apply a force along the symmetry axis from the top and the bottom? You can see it here on the sketch. What will happen? At a certain point, depending on the material properties of this rod, it will bend to one side. Can you tell me to which side it will bend if I put a symmetric force, if I apply a symmetric force onto this symmetric stick? All directions are equally likely where it could bend. So it wants to find the state of minimal energy. It wants to find the minimum of the potential. But there is an infinite set of equivalent minima. It could bend to any direction. So the minima, they form a circle. It could bend into any direction. But in the moment when it bends, it breaks the symmetry. But it means it's not the Lagrangian that would contain a potential for the force. So the Lagrangian is still invariant under the symmetry, under the rotational symmetry. But choosing a minimum is the process that breaks this symmetry. So that's the case of spontaneous symmetry breaking. And this is just a mechanical example. Yes, please?
In principle, theoretically, if we apply a force from top and bottom and it's exactly in the center, it should compress rather than bend, or?
Yeah, first it might compress a little bit, but then at a certain point it will either break or bend. Yeah. Now we assume it to be a little bit elastic such that it can bend. Okay. Yeah. But the point is that it's unpredictable into which direction it will bend, because all directions are equally good concerning the point of view to minimize the energy. Yeah. At a certain point, it will be better to bend than to be compressed, because then there's so much tension inside the material. Yes, please.
Would we assume this initial direction to be determined based on, say, quantum noise?
You mean there could be small quantum fluctuations or fluctuations in the material that will give preference to one direction? Yes, that could be if there are some impurities and imperfections, or if you don't apply the force perfectly symmetrically, then there will be a preferred direction. But this is more like a thought experiment. If everything is perfectly symmetric, if the material is perfectly symmetric and you apply your force perfectly along the z-axis.
So I'm asking if those quantum fluctuations could apply to like the actual Higgs boson.
Yes, there could be some preferences. We come to this here now in the on the next slide. So here we've already discussed that the chosen ground state breaks the symmetry. Here we look at the Higgs potential. So on the slide of this coffee mug, I left it still unspecified. I said it's a V of phi, so potential of the Higgs field. And now we look at different shapes it can take. And then we can discuss how little fluctuations maybe in the early universe, in the initial conditions of the early universe could give preference for one vacuum or another. Okay. I said the Higgs potential of the Standard Model is minimal and therefore elegant, and we don't claim it can solve all problems, but it can achieve spontaneous symmetry breaking. So, but imagine you had a potential of the Higgs field. So the field phi is a complex scalar, so it is a real and an imaginary part, and the potential could have even powers of the field. So it could have phi squared. In fact, if it's a complex scalar, it's phi dagger phi, and could have phi to the 4, which would be phi dagger phi squared. If both the quadratic term and the quartic term have a positive sign, then the potential will be the 4-dimensional equivalent of a parabola plus phi to the 4 function. So it means the origin of this coordinate system will coincide with the minimum of the potential. So it's best for the particle to sit in this minimum, which is at the origin. So there's no displacement in the real or imaginary part. But what if your potential is shaped like this, that your phi to the 4 term is positive, has a positive coefficient, but the parabola, the phi squared, has a negative sign? Then it will tell you there's a like upside down parabola in the center, but for high values of phi squared will always be larger than phi to the 4 will always be larger than phi squared. So at the outer parts, the potential will go up. But in the center part, depending on the coefficients of the quadratic and the quartic term, the quadratic term can dominate. And that means there is a maximum at the origin of the coordinate system in the plane of the real part of phi and the imaginary part of phi. But towards large values of phi, we have to go up. So that means there must be a minimum in between. And one can calculate this explicitly. One can minimize the potential and finds that there is an infinite set of equal minima of equal height that form a circle. You could imagine this as the lower part of a bottle. So this would be the ring where the bottle touches the table if you put it on the table. And all of these minima are equivalent because they have the same potential height. So if the system wants to find the state of lowest energy, all of these points on the green circle are equivalent. So you see the potential is still invariant under rotation in this complex plane. In fact, it's of 2 components of the field. Here we show only 2. But choosing one of the points on this green circle breaks the symmetry in that we fix one point, and if we then rotate the system, we would see that the point moves. So it doesn't map to itself anymore. What we also see is that the points of minimal potential are displaced from the origin. So they are called a vacuum expectation value that is non-zero. That's the distance from the origin. Okay, so once the system picks a minimum, there are two directions of motion that are possible. One are movements around the minimum. They don't cost energy because they are all on the same potential height. They correspond to massless excitations, the so-called Goldstone bosons. On the other hand, if you want to move up the potential, that costs you energy. So these excitations correspond to massive bosons. And now it's maybe misleading from the picture. You see the real part of phi and the imaginary part of phi. So if it's a two-dimensional plane plus one direction, which is the potential, it looks as if there's one direction to rotate and one to go up. In fact, there are three directions to rotate because phi is a complex doublet. So it has 4 components, 4 real degrees of freedom. And we would have to draw it, the potential as a function of 4 coordinates. So there are 3 degrees of freedom to rotate. They are the 3 massless so-called would-be Goldstone bosons because they come from the spontaneous symmetry breaking of a local symmetry. It's the local symmetry of SU2 cross U1. And these Goldstone bosons cannot be found in the laboratory. You asked, okay, how can you look in the laboratory? You wouldn't find them in the laboratory, these ones, because their degrees of freedom are eaten by making the W plus, W minus, and the Z boson massive. Whereas this excitation of going up, that's a physical degree of freedom with a kinetic term, and it gives rise to the Higgs boson mass that is proportional to this displacement from the origin. So the mass of the Higgs boson is proportional to V, the vacuum expectation value, and also the masses of the electroweak gauge bosons are proportional to V. So you can see that if there is no symmetry breaking, all these particles stay massless. And the Higgs mechanism also gives rise to the masses of the fermions via the Yokohama couplings. Is this mechanism more or less clear to you? Some of you were already experts in this. Or are there more questions concerning the degrees of freedom or which is a physical mode? If not, then let me emphasize that this is the minimal solution to say there's just one Higgs boson. And that gives mass to up-type and down-type fermions and to the gauge bosons. And it also gets mass itself. The status is that such a particle was discovered in 2012 that is compatible with the expectations of a standard model Higgs boson, but that's not a proof that it is the standard model Higgs boson. So far, it's compatible. One crucial prediction is that the interactions of the Higgs with the fermions or with the gauge bosons are proportional to the particle masses. And here we see what has been measured so far. The heaviest fermions, the massive electroweak gauge bosons, they lie on this line of proportionality, but some still have large uncertainties. So new physics could hide within these uncertainties. New physics could modify the properties within the uncertainties, and many couplings of the Higgs boson have not even been determined yet. How else is the situation experimentally? So the data that has been measured so far came out mostly as compatible with the standard model, but there are some deviations that we should monitor to see if they develop into discoveries or if they vanish, if we understand that there was a mismeasurement or if we understand them as statistical fluctuations. One critical parameter is the W boson mass. It's not an independent parameter, but it depends on the gauge couplings. And it can be that it's included in electroweak fits to include all data that has been measured so far. And CDF, a detector that was running at the Tevatron that was switched off already many years ago, reanalyzed their data more precisely and found a big tension between its data and the standard model prediction, whereas the recent update from last year from Atlas is in agreement with the standard model. So it doesn't say that there is a discrepancy between data and the standard model prediction. It could also be that there is a mismeasurement by CDF, or there is a discrepancy between different detectors. It's still to be determined. The transitions between different generations of fermions are called flavor physics. And there are many free parameters. So there's a lot that has to be measured to determine them and their relations. And there's also a place where sometimes some anomalies come out. There's a relation between decays of B mesons to D mesons and leptons in the final state of different families, and their ratios are these R ratios. And the standard model predicts these ratios to be correlated around this point. Different experiments have measured them. Some are sensitive to only one of these two parameters, some are sensitive to a combination of them. And the average is around 3 sigma away from the standard model prediction. So it could be that there's new physics in the flavor sector that influences this. It could also be that the new measurements at the future B factories will clarify this and bring it to the standard model. We have to see more data. A long-standing discrepancy between the standard model and measurements has been so far the magnetic moment of the muon. That is measured when one has polarized muons in a storage ring and measures the spin precession. At leading order, this is expected, the G is expected to be 2, so G minus 2 should be 0. But then, so that would be in the Dirac theory of fermions interacting at leading order with a gauge boson, namely the photon. Then in quantum electrodynamics, there's already a correction of the photon. Then you take electroweak corrections into account by including Z and W bosons. Then there are hard to calculate corrections from hadrons, so from the strong interaction. And it could be that new particles contribute. You just need a photon outside and 2 muons outside. And there could be new physics contributing. Has been an observed discrepancy between the standard model prediction and measurements. However, recently it has been disputed how solid the standard model predictions are, and depending on the method, they moved closer to the experimental results, where it's remarkable that the experimental results from Fermilab and BNL agree very well with each other. So it could also be that this long-standing anomaly will get smaller and more theory work is needed here. In searches for heavy charged long-lived particles at the LHC, some discrepancies showed up, but there haven't been many new results on this. But later in my lecture, I will also tell you about anomalies from the low energy atomic precision measurements, where isotope shifts in ytterbium, so that means frequency measurements of the same frequency in 2 different isotopes of the same element, yield a nonlinear relation when you have 2 different transitions and several isotope pairs that you compare to each other. The leading order prediction would be that they are on a straight line. And already data from 2020 showed for ytterbium for the first time a deviation of the measured points, these blue points with light blue ellipses, deviation from the straight fit. So with a bare eye on this scale, you wouldn't see it, but if you zoom in, you see that there's a significant deviation. And from that time on, a lot of energy and research has gone into this to find out if there could be new dark bosons contributing to isotope shifts, or if it's missing higher order corrections. Okay, so with these examples, I wanted to show you that the data is mostly standard model-like. So the standard model looks very successful at the energies tested so far, down to the precision achieved so far. But here and there, sometimes some deviations from the expectation show up, and they don't always stay. They don't always lead to a discovery. Sometimes they can be explained by missing terms in the calculation. Sometimes they are explained by mismeasurements or simply by a statistical upward fluctuation. But we also see that in different sectors of physics with different energies, from very low energy like ytterbium isotope shifts to relatively low energy of the muon magnetic momentum to very high energies like looking for heavy charged long-lived particles at the LHC, anomalies can turn up. With anomaly, I mean a deviation between the measurement and the theory expectation. So if we want to solve them, if we believe some of these anomalies are true, can we build a model that explains them without violating other measurements? That's a question. But before we want to say that any of these are real problems. We want to see what is the general indication of where the standard model is insufficient. But we also see that in times of measurements across different energy scales, we need different search strategies to look for possible signals. So from the very high energies at colliders down to precision measurements with quantum sensors. Okay, where are we standing? In the past slides, I explained how the standard model is elegant and efficient and can describe complicated interactions involving gauge bosons, involving broken symmetries, involving giving masses to the particles that otherwise would remain massless. But there are crucial aspects of our observations of particle physics and cosmology that the standard model cannot explain. So I will tell you about 6 of them here. There are more. And the question will be, what are the solutions to such problems? Can maybe one model solve several problems? And the next question is always, how can we search and at least falsify such hypotheses? Verify we can only in a limited sense, but we can find out if a measurement is compatible with a hypothesis of extending the standard model. But let's first monitor where the standard model is insufficient. So we observe an imbalance between matter and antimatter in the universe. They don't exist in equal amounts in the whole universe, even if the difference is small. So the relative difference between matter and antimatter is of the order of 10 to the minus 10. So the baryon number density minus the antibaryon number density divided by the photon number density. So 10 to minus 10 sounds like a small number, but it's a significant number. And 2 different measurements agree well on finding out this number. One is this cosmic microwave background that we saw this time slice in the early universe from where on the photons propagate freely. That helps, so measuring the different angular distributions helps to determine the amount of matter over antimatter in the universe. And another method is to look at the abundance of light elements. And these 2 very different measurements come to the same conclusion that there's more matter than antimatter in the universe. Even if the difference is small, it's relevant to even explain our bare existence, because equal amounts of matter and antimatter would result in the annihilation of matter and antimatter into radiation. A second big deficit of the standard model is that it doesn't provide a dark matter candidate. And that's a problem because we conclude that only less than 5% of the energy content of our universe are comprised of ordinary matter. We call it also baryonic matter. And more than a quarter we consider to be dark matter. And the remaining overwhelming part is dark energy. Dark energy would be a topic by itself. Here we'll focus rather on dark matter. It's also more than a quarter of the pie that we still need to explain. Why are we concerned that there is dark matter? So we see it from its gravitational interactions that there must be more matter than ordinary matter in the universe. You probably know this picture from the rotation curves of spiral galaxies, where the expectation of the rotation velocity as a function of the distance would be predicted to fall off, whereas the observation over different distances results in this curve. So there needs to be more matter in the center of the spiral galaxies, more material. So because we cannot see it via the visible interactions, we call it dark matter. We could say, okay, it exists, it interacts at least gravitationally, we are okay with that. But we are more curious, we want to know what is the nature of this dark matter. Is it a particle? Is it several particles that together bring up this energy density that we need? How does it interact? Is it described by a new symmetry? Or is it described by some other mechanism? That would help us to also have an elegant theory of not only these 5%, but also these 27% over there. So a lot of effort are going into finding suitable candidates for dark matter and searching for them. You mentioned already neutrinos, and neutrinos are predicted to be massless in the standard model. However, expectations show that neutrino generations fluctuate into each other, they oscillate, here in this case from the second to the third generation of muon neutrinos to tau neutrinos. And early evidence was already in 1998 to see that the data, these red crosses, agree with the hypothesis of oscillations in green and don't agree with the expectation of no oscillations. And oscillations are only possible if the neutrinos have masses, and we still need an explanation for those. Another deficit of the standard model is that it enters so many new parameters in the flavor sector. Flavor, as I explained, means transitions between different generations of fermions. And they occur in the lepton part, namely where the different neutrinos oscillate into each other. And their oscillations of the interaction eigenstates, the electron, the muon, and the tau neutrino, into the mass eigenstates, which are combinations of these three. They're called nu1, nu2, nu3. This matrix forms this pattern with a relatively democratic pattern with one very small entry and the others sizable. Whereas the mixing pattern in the quark sector is very hierarchical. So the quarks rather mix in with or stay in their own generation and don't mix so much across generations. Yes?
Question, you were talking about some eigenstates, like eigenstates would be Lagrangian?
Yes.
Okay.
Mm-hmm. Yeah. So these are the eigenstates with a label of flavor. They are the eigenstates, how they appear in the doublets of SU2. So they are the SU2 eigenstates. And if we measure a resonance, that means we measure something corresponding to a mass, and that we call a mass eigenstate. And the mass eigenstate doesn't necessarily need to be an eigenstate of that interaction, but the mass eigenstate could be a superposition of the different interaction eigenstates, a linear combination. So that doesn't even require quantum field theory, that can also already be like in a quantum mechanical sense. So that means one first needs to diagonalize a mixing system, so a mixing matrix, to find out the mass eigenstates. And there are still different hypotheses in which order the mass eigenstates are composed. And the same applies to the quarks. They also have their interaction eigenstates, and they mix into the mass eigenstates. And that mixing is governed by the so-called CKM matrix for Kabibo, Kobayashi, Masukawa, whereas the neutrino mixing is described by a different matrix, the Porvo-Makagara-Naka, or I think I can't pronounce it right now. The Maki-Nakagara-Sakawa matrix, yes. They have quite, as you see, now this is just a graphical representation roughly of the sizes of these entries of the matrices. They have very different patterns, but each matrix itself already gives us puzzles, why it is like this, and why are they so different. So we could say, they are free parameters, fine. One has to measure them, fine. But it means we accept that the Snell model, which is otherwise very elegant, introduces many free parameters in the flavor sector. And as physicists, we rather want to have an explanation for that, at least try to find out if there's a symmetry principle or an ordering principle that describes the hierarchies of the mixing patterns. So we don't really call it a problem, we rather call it a flavor puzzle. So, to say there's no discrepancy between, or it's not a real problem to have these mixing patterns, but it gives us a puzzle. Another one is, it goes backwards. The hierarchy problem of the Higgs mass. So we saw that the Higgs also acquires a mass proportional to the vacuum expectation value of the spontaneous symmetry breaking. And we measure it to be around 100 GeV. It's 125 GeV. Another scale of physics is the Planck scale, where gravitational effects play a role. And by itself, there's no problem that there are two different scales in physics. But what is puzzling is that as an elementary scalar, the Higgs boson is quadratically sensitive to anything that couples to it. So it could couple here to the fermions of the Standard Model, but also new fermions or other particles. And we could close these two legs into a loop. So that is a correction to the Higgs boson propagator and therefore to the Higgs boson mass. And we expect the Higgs mass to grow proportionally to the mass scale squared of whatever runs here in this loop. So if there's no new physics until the Planck scale, if the next new physics effect that happen after the weak scale is gravitation, then we would expect that the Higgs mass is driven up to the Planck scale by these so-called quantum corrections, by calculating higher terms in the perturbation series. But we still observe the Higgs boson at the weak scale. So there's the question, what happens there? Is there a mechanism that maybe introduces a new term that cancels exactly this large contribution to stay at this scale? But if we add some 16 orders of magnitude and we need to subtract 16 orders of magnitude, that means we need a fine-tuning of this cancellation of 16 orders. And that could be, but we would want an explanation for that as well. So the question is there symmetry that protects the Higgs mass to stay where we measured it? Or is there maybe a dynamical process that explains why in the evolution of the history of the universe, the Higgs mass is at this value that we measured? Is this problem clear to you? Yes. There's another challenge, namely the strong CP problem. We discussed only briefly the strong interaction because it is not broken, so we didn't involve it in the electric symmetry breaking. It could have a term, we will come to it in more detail later, that could contribute in principle. It's a term of the gluon field strength times the conjugate gluon field strength. And the coefficient of that term could in principle be 1 if no symmetry suppresses it or forbids it. But the neutron electric dipole moment limits this coefficient to be smaller than 10 to minus 10. So it could be, we could still say, it's like it is a free parameter, maybe it's just small, but we could also say, it's a bit suspicious if a parameter has to be 10 to the 10 times smaller than we would naturally expect. So maybe there's also a mechanism to explain this. So these are already 6 evidences that the standard model is incomplete, that we need some new physics to extend the standard model. And if we do so, we should derive from our extensions if we expect new particles, if we could predict in which mass range they would appear, which coupling strengths they could take. Could also be that we extend the standard model by changing the geometry of spacetime. And we should check if we find suitable observables in the laboratory to test these hypotheses, to maybe rule them out or to find some signal that is compatible with the hypothesis. Okay, so now we will go a little bit into approaches to models beyond the standard model. Most of you said you haven't yet studied so much beyond the standard model. So this is what we will still do before the break to see how we can extend it. One possibility is that we say, the symmetry. Yes, please?
Yeah, I was just wondering, so in the list of all those problems with the standard model, it didn't really mention that it doesn't include gravity, but is it like a whole problem?
Yes, yeah, that's like the elephant in the room that I didn't even mention, but you are completely right, yes. So we know 4 fundamental interactions so far. The strong interaction and the electro-weak interaction, that are 2, like the weak and the electromagnetic interaction. That are described elegantly by the standard model, but we also know gravity. That's the most obvious thing around us, and the standard model cannot include this. It cannot include gravity in the formalism of a relativistic local quantum field theory in 4 dimensions, so not as a gauge theory. So it's still unclear if there's an exchange boson for gravity, if there's a graviton. There are approaches to quantum gravity, also how to quantize gravity, how to make a quantum field theory out of gravity. That's still an open question, and there's no way yet how to unify the 3 interactions of the standard model with gravity. So that's an obvious loophole of this, or deficit of the standard model that it cannot do. Yes, you're completely right. And there are, of course, studies of gravity itself and the consequences of gravity and checks for deviations from general relativity, consequences of gravity in terms of gravitational waves. Gravitational waves are also signals that one can possibly detect with quantum sensors. And on the theory basis, there are attempts to loop quantum gravity or theories that unify both aspects, like all four interactions. Yes, please.
So from what I see, it seems like the standard models has a lot of problems.
Mm-hmm.
Like maybe this is more of an opinion-based question, but in your opinion, what is there a point in still sticking to the standard model and trying to find like ways around it, or
Yes.
do you think I don't know, does experiments need to be just more sensitive? Like, what is your opinion on this, or do you think the standard model is more of like an approximation, and for a really accurate description,
Yes.
we need to think of something completely different outside of the box?
Absolutely. So what you just said is especially the last point, is very true. So you say maybe the standard model is an approximation, and this is how we think it should be. Because on the one hand, we see this list of deficits, and on the other hand, we see that at the energies tested so far, from low energy precision measurements to collisions of protons at 13.6 TeV, most measurements still agree with the standard model. So apparently it approximately holds, but we know it has to be extended. So with extend, we mean we consider the standard model as an effective theory. One can do this very systematically in the framework of effective field theories. So we say up to a certain energy range, the standard model is the description, and the particles of the standard model are our relevant degrees of freedom. If we go to higher energies, the standard model is not the theory that describes the world anymore. At higher energies, there could be other resonances, other excitations, in other words, other fields, other particles that contribute. But their effects, if we come from the high energies down to the low energies that we have, relatively low energies that we have measured so far, at the energies measured so far, the effects of these new particles are so small that they haven't been resolved yet. That's the philosophy. There's also a limit towards, if we go from the standard model to even lower energies, so below the proton mass, or below the QCD scale, then the quarks and gluons are not the 3 degrees of freedom anymore, but they form bound states of hadrons. So then one can formulate a low energy effective theory. So one can, in an elegant way, always say, in this energy step from there to here, this is the theory that is effectively true, that describes my dynamics. From there to here, it's maybe the standard model. But beyond the several TeV scale, we should have a new theory. So we have tested the standard model up to several TeV. Could still be that some assumptions were too simplified, and the exclusions we have put, for example, on supersymmetric particles, don't hold in each and every realization of supersymmetry. But we could say if there's, for example, supersymmetry or new extra dimensions, they must be heavier than the scales tested so far. And below these scales, the standard model is a good description. So whenever we build a new model, even if we start from high energies, we say we build a grand unified theory where all interactions meet at high energy in one point, so we don't have 3 different gauge couplings, but only one. But if we evolve down these couplings, down to the scales we have measured so far, we must recover the standard model. Otherwise, we build problems with the measurements that we have collected over decades. But that was a very useful question. Thanks. Yes, please.
Maybe also a general question. The standard model, so, okay, it explains like groups of particles and subparticles, but is the standard model a group by itself? Let's say a mathematical group theory?
Yes, mathematically, the standard model is described by a gauge group. This is this product group I showed. That's a group by itself. So it's a group by several generators. And at energies above the electroweak scale, so above the masses of the Higgs boson, the symmetry is exact. And if we come to lower energies, we see that it's broken.
So, for example, we are searching, let's say, for the emergence of new particles, and could that
Good question. But even after the symmetry breaking, it's still a group, but it's a subgroup of the original group. But it's still a group, yes. You are asking, could there be extensions of the standard model that will not make it possible, that will take away this possibility of having a group? Yes, so there can be extensions of the standard model that are not based on symmetries, so that's the next slide. So I will explain to you that there are two ways of extending the standard model. One, at least two, based on symmetries. So we would say the total group describing our world is the standard model group times a new group. And the product would still be a group. Another mechanism that I will explain in a bit is when it's not based on groups. Yes?
Since it's not a generator, mathematically, what object can you pair the Higgs boson to?
So we always have to form singlets in the combination such that the Lagrangian is a scalar number. And the Higgs boson itself is a doublet of SU2. So we have to have a phi dagger phi such that we combine it into a number. We could couple the Higgs boson to the Higgs boson that looks like the Higgs boson of the standard model to another Higgs boson. There are theories that have several Higgs bosons that start from several Higgs doublets. And there could be, for example, Higgs 1 dagger times Higgs 2. And that would be combined. So thanks for all these questions. Are there more before we continue into this model building? But then maybe we will see your questions step by step. So one possibility is to say, yes, we have been so successful in building theories that come from mathematical principles and actually have something to do with what we observe in nature. This has been a recipe of success so far. We want our extension of the standard model that address this list of questions that I show you, this list of deficits, also by symmetries. One possibility would be to say, we introduce a new symmetry. Symmetries impose constraints on the way how couplings and masses can behave. We could introduce a new symmetry that enforce relations between couplings and masses of the particles of the standard model. We see them here, the Higgs in the center, the gauge bosons here, and then the fermions around. We could mirror this standard model and put partner particles. And we could say the coupling of these partner particles are related to the couplings of the original particles by a symmetry. So they are not free parameters. That would mean we don't double the number of free parameters, but they are related. And that could help in particular with the hierarchy problem of the Higgs mass. Here, this slide is somewhat slow. Okay, so that could happen if we have a fermion of the standard model here in the loop, then we introduce a partner fermion of the extension that introduces a contribution exactly minus the one of the standard model, then these two quadratic terms to the Higgs mass would cancel and would explain why the Higgs mass stays at the mass where we are. And this mechanism is realized in supersymmetry. Who of you has heard about supersymmetry? Many. Yes, it's a beautiful theory coming from mathematics and addressing several problems of the standard model by solving the Higgs hierarchy problem in case the supersymmetric partner particles have the same masses as the standard model particles. Unfortunately, at these masses, we haven't found the SUSY particles yet, the supersymmetric partners. So if supersymmetry exists, it must also be broken, and there are different mechanisms of how to break it. And the more we break it, the heavier the new particles become, but the less precisely they solve the hierarchy problem. So the higher the energies we push when we observe at the LHC, the less attractive supersymmetry becomes, but it's still a possibility. Maybe it could solve the Higgs hierarchy problem between the electroweak scale and few TeV, maybe 10 TeV, and after that we need some other mechanism to explain the remaining hierarchies between, let's say, 10 tera electron volts up to 10 to the 18 GeV of the Planck scale. In addition to supersymmetry, there's also a mechanism called neutral naturalness, where where the standard model particles also get partner particles, but not necessarily color charged. Another mechanism is based on dynamics. So there the question is, if I measure a certain parameter, for example, the Higgs mass, in my Lagrangian, it's a free parameter. It can take any value. It cannot be predicted by the standard model theory, so I have to measure it. Then the experiment tells me a value, and I could say, okay, I'm happy I have that value. I don't need to explain it. But as I mentioned, especially in the flavor part of the standard model, there are so many free parameters of all the mixings and all the masses. We are a little bit unhappy to have so many free parameters in our theory. Our ansatz is the less free parameters we have, the more predictive the theory is. So the less measurements we have to do to predict something new and test if this prediction agrees with our previous measurements. So one solution is that we say these parameters are actually not free parameters, but they are expectation values of a dynamical field. So what if I have a field that can move inside its potential? And it's just best for this field to go to its minimum. And the value that this field has at its minimum corresponds to the measured value of something. So that would mean, applied to the Higgs mass wouldn't be a free parameter, but would be determined by the minimum of another particle. That would mean we have to introduce a new particle. Instead of having a free parameter, we would have an additional particle, and its vacuum expectation value would tell us the Higgs mass. Or we could also introduce a new field for the free parameters of the flavor sector and see if they can be explained by such a mechanism. So examples are the so-called axion. We will see it because it's one of the prime examples that is currently being looked for with quantum sensors. The axion is a solution to this puzzle of the parameter in the QCD Lagrangian, a parameter that could be 1, but it has to be now smaller than 10 to minus 10. And another example is the relaxion. That's a new field. Relaxion. It's an analogy to the axion. The axion is a scalar, it's a pseudoscalar, so it means a spin 0, but it behaves odd under parity and even under CP, under charge and parity. And the relaxion is similar to it in that it's also a pseudoscalar. Who is familiar with scalar, pseudoscalar, vector boson, axial vector, and this? So that's how a field transforms under Lorentz transformations. For sure, you learned about Lorentz transformations and special relativity. And when we describe a quantum field theory, we always need to know in which representation of the Lorentz group our fields live, so how they transform under Lorentz and Poincaré transformations. So that's the question, how do they transform under boosts, rotations, and translations in space-time? And the scalars are the ones who live in the trivial representation, so that means they transform trivially, only their coordinates transform, but the fields don't transform. And the pseudoscalars, they transform. They are also like scalars, but they transform differently if you flip the charge and the parity. There was another question. Or not? Yes?
Yeah. Could you elaborate a bit more on how the fields are dynamical?
Dynamical means they have a kinetic term. So if for a scalar, it would be d mu phi, d mu phi. Maybe in the coffee break, maybe we have the chance to write down something on a sheet of paper or so. That means they, you would look, so what you do is if you have a Lagrangian, you can apply the Euler-Lagrange equations as in mechanics, and you get so-called equations of motion that are differential equations on the field. And then when you solve them, you get a solution how the fields evolve in time. So they are dynamic, they're considered dynamical if they have a kinetic term. So if they're equations of motions no, I forgot the word, I just said it. Differential equations contain also the derivative of the field. So if they have non-trivial equations of motion. And okay, we were speaking about the axion. The relaxion resembles the axion in that it's also pseudoscalar. And the rel comes from relax because it relaxes the Higgs mass. That's this principle here of the relaxion. I can tell you much more if you like. Now I keep it short. The idea is that we introduce a new field. It's also it's now this pseudoscalar field phi. It's not the Higgs boson, but it first starts rolling down a linear potential in the early universe, and then at a certain time, it starts developing oscillations in the potential. And the question is, where will the relaxion stop? it will stop when the derivative of the rolling balances the derivative of these oscillations. So it will be trapped in one of the minima. And the interesting idea of this model is, that was proposed almost 10 years ago, but it's still a relatively new model, or considered a relatively new model, is that the Higgs mass depends on the value of the relaxion field. So it depends on where the relaxion field stops rolling, and we read off the value where it stops, so where it's trapped in a minimum. And if this value corresponds to the observed Higgs mass, we have solved the Higgs hierarchy problem without needing a cancellation, but by introducing a new field whose evolution in the history of the universe then determines which mass the Higgs mass has today. That also means that the Higgs mass hasn't always been constant. It means that the Higgs mass has developed over time in the evolution of the universe, and today has the value we have measured now, thanks to the relaxion. So it's a trade-off. It says we get rid of a free parameter. On the other hand, we introduce a new field. So we make the model more complicated, but more predictive. And then it's our task to look for the relaxion. And that's also being done at colliders, in cosmology, and also with quantum sensors. So there are maybe more approaches, but these are the two main categories that we usually apply to extend the standard model, always with the philosophy to say, at the energies measured so far, we should recover the standard model. Otherwise, we create problems with the data so far. But we need to extend it. You saw this list of at least 6 problems where we haven't even mentioned gravity, that we really need to do something. Otherwise, we have to swallow to say, okay, there's dark matter, but we don't know what it is. Yes, please.
So the Higgs mass was changing over time.
Yes.
In the past. Does that mean that then the standard model was also very different?
Yes. Yes.
It's like Lagrange balancing.
The standard model was, from the equations, similar, but the masses of the gauge bosons depend on the vacuum expectation value of the Higgs. So therefore, also the gauge boson masses and the fermion masses were different, while the relaxion hadn't yet reached its final point of the evolution.
And there's no way to measure that, right?
There is.
Can we measure that?
Yes, yes. So there, then it's important to think of all consequences. If we introduce such a new pseudoscalar, it could also influence the evolution of the early universe. If we inject a new pseudoscalar, it could also decay into even lighter particles, so we could find them. Or it could modify the cooling of stars. Also, astrophysics helps to look for it. If you have a star, it loses energy. But if you have an additional light scalar or pseudoscalar, it could also dissipate such a new light scalar that would carry away energy from the star. And by measuring quite well in astrophysics the star cooling rates, you can say at least a new scalar or pseudoscalar cannot have taken more energy away than the amount constrained so far. Also, if it's heavy enough, you can look for it at colliders, but it could be very light, so it cannot be observed. You could also see what consequences would it have for the evolution of the universe if the gauge bosons had reached their values of the mass only later or only gradually. And all this is being done. So the parameter space of the relaxion is constrained from different corners of putting constraints from everything we know today. Because it's such a attractive or thought-provoking model, so different than supersymmetry, that since then a lot of activity has gone there to see if it could be viable, because if yes, it would be quite an interesting solution, but the more we search for it, the more the room shrinks. But there's still a natural parameter space left open, and at the end of the talk I will speak, for example, about a nuclear clock that could also help to look for it, to close the gaps. Yes. Okay, so these are the big approaches. Now I'm looking. Now we are approaching 3:30, so somebody will interrupt me when we go for coffee, or we could also.
How much time do you need?
So for the first part, I have a few more slides of introducing. My goal was before the break to say what are the things we want to look for, and after the break, how do we look for them? Good. We already came a little bit to it. Now I wanted to inject a little bit more theory thinking, such that if we look for new particles, we know if it's like looking under a lamppost when we say we have these experiments anyways, or they are built on the way to build a qubit, we can use them as quantum sensors to look for something, then it's already good to do it anyways. But I want to emphasize that the things we can look at are even well motivated from the theory. From what I have said so far, it could have been clear to you now that there's not the one prescribed way how to extend the standard model. There are different ways to extend it, by symmetry, by dynamics, by heavy particles, by light particles. So we could now continue in different directions to motivate more heavy particles or the light particles. Now, because the quantum sensors are particularly sensitive to light particles, we focus a little bit on where could light particles arise? Would they have to be engineered quite a lot in their Lagrangian, or could we naturally expect them? So we already made use of Goldstone's theorem when we discussed the picture of the symmetry breaking of the Higgs potential. But here I wanted to come back to it and tell you maybe the foundation of it. If we break a symmetry, we expect to introduce a new massless scalar, so a spin-zero boson. You already asked what does it mean to break a symmetry, and I said to be precise, it means if we break a generator of a symmetry, that means if the Lagrangian is not invariant anymore under the transformations of this one generator. So per broken generator, we expect a massless spin-zero particle. And this applies to global symmetry, so where this transformation parameter doesn't depend on the space-time coordinate. But we also saw that if we break a local symmetry, it's a would-be Goldstone boson that gives rise to the massive degrees of freedom of the gauge bosons. But here, if we look at global symmetries, we really expect a new massless particle for every broken generator. So that means we should watch out for like copies of the photon, lots of massless, not the photon has spin 1, but we should look for lots of massless scalars. But why did I show you in the beginning this parameter plane of unknown masses and unknown interaction strengths? In fact, it's not as strict. We don't only look for massless particles, we could expect light particles. So if we have an exact symmetry and we break it spontaneously by this mechanism that I described by this rod and also by the Higgs potential, we expect massless particles. But if the symmetry we start with is only approximate, so if it holds as an approximation, for example, if we say the masses of the up and down quarks are so light, they are much lighter than the Higgs mass, than the electric vacuum expectation value, we could say they are approximately massless. In fact, there is an explicit breaking by these mass terms, but we could treat it as approximate. So if we start from an approximate symmetry and then we break it spontaneously, we expect the new particles to arise, these Goldstone bosons, not to be massless, but to have a small mass. And this small mass depends on this breaking from where we started from. So that means we are not restricted to really look for massless particles, but it's very well motivated and generic that if we start from an approximate symmetry, we could expect low mass particles. Examples are a particle that comes from a symmetry if we impose invariance of our theory of a scaling, the dimensions of scale invariance. That's the dilaton, or it's called conformal invariance. We could have a new spin 1 particle that resembles the photon that comes from a new force, so introducing a new U1 gauge symmetry. And this new hidden photon would mix with a visible photon, and we could constrain the mixing parameters, and we could look for this dark photon. We mentioned the axion, we will come to it in more detail. That is proposed as a solution to the strong CP problem and can simultaneously be also an excellent candidate for dark matter. And in fact, there's still a lot of unexplored space, both in the model building and also for a concrete model and the parameters that that model could have. And we need the interplay of cosmology, of precision laboratory probes, and of the intensity frontier to measure such rare processes of light particles frequently. Okay, so that's kind of the paradigm or the theory foundation. And now we come a bit closer to dark matter models. So if we now say, out of this list of 6 or with gravity 7 problems that the standard model cannot solve, we want to address the problem of dark matter. Where should we start? Dark matter, there's not the one model for dark matter. We could say we have dark matter coming with a model coming from the weak scale. There, so relating to the scale of the Higgs mass. If we introduce supersymmetry, the lightest supersymmetric particle would be a dark matter candidate because it cannot decay further and it would be dark to the interactions we know so far. In extra dimensions, we could have whole towers of new particles, out of which some can be the dark matter particle. Little Higgs is also a symmetry extension of the standard model. An effective field series where we say up to a cutoff the standard model is valid, or we can build simplified models where we don't take all degrees of freedom into account, but only a few, or we classify them in some classes. So that would be dark matter expected at the weak scale. Could dark matter be connected to neutrinos? Could it be a sterile neutrino? What if we introduce light bosons, like the axion or similar axion-like particles? We mentioned the QCD axion. We could also replace the paradigm of dark matter by modifying gravity. So that was extending the standard model by changing the geometry. Could dark matter maybe be very heavy? Then it could be primordial black holes. That would be the heaviest dark matter candidate we can imagine. And other particles that don't fall into these classes. So if we now wonder, this is the landscape of models developed so far, and not even complete, of dark matter. They map onto different mass regions. So the physics we describe in the standard model goes roughly from the GeV scale, so the mass of the proton, to a TeV, roughly. There we describe the standard model. We know particles below the GeV scale where the quarks and gluons are not the degrees of freedom. But the scale that can be covered by dark matter models is much broader. So until recently, WIMPs were the favorite candidates of dark matter. That stands for weakly interacting massive particles that have where the weak interaction corresponds to a cross-section of dark matter annihilation and creation that would be compatible with the observed relic abundance of dark matter today. But they are predicted in this mass range, and they are still being searched for. They are not excluded, but the simplest models with a significant interaction strength are apparently not realized. Then dark matter could be heavier than that, up to primordial black holes, or could be lighter than that. In this KV to GeV mass range, we meet the concept of dark sectors, so that dark matter, there's not only one dark matter candidate, but could be several dark matter particles that make up a dark sector, and they could interact with the standard model via portals. We come to this. Or it could be much lighter. We call it ultralight dark matter. That's so light that it forms classical waves of coherent oscillations in space-time. But maybe we need a coffee break soon. Let me check how many. Now there are still a few slides, so maybe we do this after coffee. I think otherwise the concentration will drop. Then we will jump after coffee right into the axion as an example for dark matter. I will explain to you what I meant with a portal to a dark sector, and then I think we are ready to really address the sensors that we can use to look for them. Thanks already for all your questions. Welcome back. I hope you are refreshed and you are also convinced that we need physics beyond the standard model after all the work we did before the break. So now we will finish looking into options of how to extend the standard model, and then we switch to the second part where we discuss in more detail how to look for signals of such extensions of the standard model with quantum sensors. So here where we stopped was to look a little bit more closely at the strong CP problem, because that brings us to the axion, which is one of the favorite dark matter candidates that is extensively looked for with quantum sensors. So I decided to maybe invest a slide on this. So I mentioned only in this box of the list of the 6 problems plus gravity that we had, that there is a term in the Lagrangian of the standard model, particularly of the strong interaction, that can have this parameter theta in front. What is this term? So it's a product of the gluon field strength tensor G mu nu times its dual, the G tilde mu nu. So that's a term that violates the product of charge and parity flip. So that is not invariant under flipping, the product of C and P, but but that's okay with QCD, with a series of strong interactions. A priori, so we have this structure of the field strength tensors that come out of the group theory. We have some coefficient determined by the gauge coupling G, the coupling of the strong interaction, and we have a free parameter in the front that quantifies how strong this term is. If there's no symmetry that tells us that theta should be extra large or extra small, we would assume naturally it could become order 1. If it's order 1 or at least not totally suppressed, we would expect to measure such a CP violating effect. In particular, we would expect to measure an electric dipole moment. That is, the electric dipole moment D is the displacement of two equal charges at a distance. And why is this interesting? It's if we measure electric dipole moment of a neutron, of an electron, also of molecules, that's a sign of CP violation. In the standard model, there's also a tiny bit of CP violation. There are two parameters in the standard model that can violate CP. One is this QCD term with a theta in front. The other is the one phase that we can have in the CKM mixing matrices of quarks. That's a 3x3 unitary matrix. If you do the math and you calculate how many free parameters there are, you can find out that there are 3 rotation angles and 1 complex phase. So, but that's so small that all predictions of electric dipole moments in the standard model are smaller than the current experimental uncertainties. But in case this theta angle is really order 1, we would be able to see something in the measurements of electric dipole moments. Yeah, they are interesting because flipping C and P then would flip C flips the charge and parity flips the space. If we assume CPT is conserved as it should be in a relativistic local quantum field theory, then that and CP is violated, then T should also be violated. So we can relate these transformations to each other. Okay, but what is the fact is that if we measure precisely the neutron electric dipole moment, which is sensitive to interactions of the quarks and gluons, if we measure it, we only find an upper bound. So there's no value of the neutron EDM that we can distinguish from 0. We can only place an upper bound on it. We say it's 0 plus the uncertainty. So if it exists, it must be smaller than the upper bound on the neutron EDM, and that translates back into this theta, or a bit modified theta parameter. That's now this theta parameter standing in front of this term, times a phase from the quark matrix. This combination has to be smaller than 10 to the minus 10, where we expected it to be of the order of 1. So that tells us it's much smaller than we expected. We could again say, it's just a parameter, it's determined to be like this, fine, but we could also say, it smells a bit like this hierarchy problem of the Higgs mass, where we would expect the value to be naturally larger, and it's many orders of magnitude smaller. So we are unsatisfied with just accepting this value. We could do, but we could also say we want an explanation for this. So the goal is to build a model that can explain this value. And you saw this list of at least six deficits of the standard model. If we need 6 different models to address the 6 different questions, then still we won't have a unified model that solves all problems. To date, we don't have any model that solves all open problems of the standard model plus includes gravity. But it's attractive to build a model that can solve more than one problem. And such a solution could be the axion. So, there was a mistake of the overlay, sorry. The standard model contains this term that we just discussed. And why is it so small? The solution could be that this parameter is not a free parameter, but it falls into the second category of how we build models. It could be the expectation value in the minimum of the potential of a new field called A. Then we call it the axion. So theta is something dimensionless. The axion A would be something of mass dimension 1. So we divide it by an energy scale F. So it also has the dimension of mass or energy. If we set h bar and c to 1, masses and energies are the same for us. And how do we see it's a dynamical field? We also add this kinetic term in front, as I mentioned before. Somebody asked when do we call a field dynamic if it has this kinetic term. So we say that we introduce a new pseudoscalar field, so spin 0, but a CP odd. So odd under CP transformations. It's called the axion. It depends on it's not a parameter, it's a field in space-time. And if it has a potential that becomes minimal at this value, which is the ratio of its field over this energy scale, minus this phase of the quark matrix, if it becomes 0, if the potential becomes minimal at this value, then it would explain why theta bar is 0. And maybe there's a small deviation from this. Maybe the axion fluctuates a little bit around its vacuum, so it doesn't need to be forced, theta doesn't need to be forced to be 0, but it would be compatible with theta bar being smaller than 10 to minus 10. So what have we just done? We have replaced, as in the discussion of the Higgs mass, introducing the reduction here, we reduce the theta parameter by a dynamical field. So we have one free parameter less, but we have the prediction of one additional field, and then one should look for it. And how to look for it is, one possibility is to see if we have now a Lagrangian at high energy, like a relativistic Lagrangian, we can take the limit at low energy and become to a non-relativistic Hamiltonian that describes quite explicitly how to probe the axion couplings. So it says the axion, the A, should couple to a pair of photons, and we should look for it via the interaction. Now we go from the field strength tensor of the photon back to the E and B fields, the electric and magnetic fields. It should couple, the axion should couple to a pair of fermions, and we can look for it via its spin. And it should introduce an electric dipole moment, so we should look for the projection of the spin to an electric field. So that's then a way, how to say, we introduce a model that solves one problem, namely the strong CP problem. We make a prediction there should be a new particle, so we should, and here's a kind of a recipe how to look for it, what are its interactions at low energy. And then it turns out the axion would also fulfill requirements to be a dark matter candidate, so to have a remaining number density today that could account for these roughly 26% of the energy content of the universe. So if we introduce the axion to solve one problem, we get a solution to a second problem for free, and that's why we find it so intriguing. A lot of work is currently going into axion searches and also axion model building. Please, you had a question.
Yes, but now we are also introducing a new parameter FA, right?
Yes.
So not really reduce the amount of parameters.
Yeah, good observation. Yes. So this FA is resembles with this decay constant of pions. Pions are composite particles of quarks, and they describes the scale at when they decay or what their masses are. Indeed, there is a new parameter, but the good thing is that the mass of the axion is not another free parameter, but the mass of the axion is then determined by the scale FA. So we still have a new parameter, but we could verify this, or not verify, but at least exclude or check for compatibility of this mechanism with searching for a new particle. So if you find a new particle, probably you wouldn't complain anymore about having this FA parameter, but you are right, this is still a parameter. More questions or concerns? Okay. So that would be one model that can solve several questions. I mentioned already this concept of having a portal to a dark sector. So in the beginning I said, we see there must be dark matter or a modification of gravity because of the gravitational observations. So if we consider it to be a particle dark matter, we call it dark because it doesn't interact via the known interactions. How can we then observe it apart from its gravitational interactions? If it doesn't couple at all via the strong and electroweak interactions, we won't at all be able to test its interactions with like standard model particles in our laboratory. A model or a framework that solves this problem is to consider a portal, to have some intermediate particle that can couple to the hidden particles, and we don't. It would be like a oversimplification to say all the dark matter content must be provided by one dark matter species. We see the standard model contains many particles. Could also be that, and that's just 5% of the universe, energy of the universe. So this 25% could also consist of several particles. This translates in like this, what the picture we had before. Now it's flipped up and down. If we have a dark sector and a visible sector, which is the standard model, we could introduce a mediator particle that couples with a not suppressed coupling to the dark particles. And this mediator is not completely a dark particle. It can mix with particles of the visible sector and therefore has a small coupling to the visible sector. So effectively, the dark particles can couple to the visible particles of the standard model. But via this indirect effect, the couplings would be very small. We would expect small couplings. And the mediator could be different, different options. It could be a scalar particle of spin 1, spin 0. It could be a vector particle, vector boson of spin 1, coming from a new gauge symmetry. Or it could be a vector boson that mixes, for example, with a photon. If we have the dark photon and the visible photon, they mix, and their mixing parameter introduces this feeble interaction. Okay, so if we have these three options for a mediator, one job is to also look for this mediator and also look for the interaction of the mediator with a dark sector. But first of all, look for the mediator where we have a chance to find it because it couples to the visible sector. And here we look at these possibilities that the mediator is relatively light. So we already start in the sub-eV mass range. For comparison, the proton is around the GeV mass range, so 10 to the 9 eV, and the Higgs at 125 GeV. So here we are really low mass options, and they would leave the detectors of colliders undetected. And a better way to look for them is to really look at low energy probes where the scales are more of the energy ranges are more similar to the ranges of these long range interactions. So what do we have here? We see in the different colors which of these mediators can be found, and here we find many quantum sensors and other tabletop experiments. So an advantage of such light particles is also that we might not build huge accelerators to reach the energies to produce them, but lower energies are enough to produce them, and small laboratory experiments have a chance to find them. We saw these interactions via the spin-based sensors, optical interferometers, that means photon interferometers. We also can consider atom interferometers. That's the idea of using interferometry as it's in the Michelson-Morley experiment, and how LISA works as one of the major gravitational wave detectors. But instead of interfering photon waves, one would interfere matter waves of atoms. And here we come to a big chapter that also covers a quite broad mass range of atomic, molecular, and nuclear clocks, and this is something we will focus on in the next slides, to see if such new particles can disturb the transition frequencies of precisely measured transitions in atoms, in molecules, or in nuclei. Then here we have at a bit higher mass ranges, quantum materials. A very important class of experiments are cavities, where a mode of a new particle could be resonant with a cavity mode, and therefore be looked at with precisely tuned cavities. Also, mechanical resonators can be sensitive to such mediators. And here, over this broad mass range, you see the so-called EP tests. They are tests of the equivalence principle, the weak equivalence principle of gravity, to look for fifth forces that deviate from the known laws of gravity. They can happen, so they work with pendulum experiments at small scale or even on galactic scales. So these are signals we want to look for. On the other hand, we also want to look for gravitational waves. So far, we have not commented much on gravity, But we saw in one of the first slides that gravitational waves propagate from very early on in the universe, undisturbed until today. So they are really messengers of the early universe, and they can tell us about processes in times shortly after the Big Bang, also often related to phase transitions. So we can also study gravitational waves to learn about the transition from the unbroken electroweak phase to the phase where the Higgs boson develops a vacuum expectation value. And there are other phase transitions in nature that might trigger gravitational waves, so violent processes kind of that make the space-time, that perturb the space-time. And then gravitational waves are created as perturbations of the metric. And quantum sensors that are developed in particular for axion searches are often also very useful to look for gravitational waves, especially also in ranges where other gravitational frequency ranges where other gravitational wave experiments are not successful. Okay, so to conclude a little bit our first part of the lecture, here I mention some of the problems that we discussed before. So the particle questions that keep us busy are to explain why we have more matter than antimatter in the universe, what is the particle nature of dark matter, if it's a particle, how to solve the strong CP problem, how to explain the Higgs mass so many orders of magnitude below the Planck scale, to explain how the electric phase transition happened. Was it really as in the standard model, or is there a more complicated Higgs potential? Why do we have neutrino masses? And before we even didn't discuss so much dark energy, also gravity. So let us now transition to the next part of the talk. How can quantum sensors help us to address these really relevant questions? So this is by far not a complete overview, but we already saw that electric dipole moments are sensitive to CP violation, at the example of the neutron EDM. But we can also use these EDMs in a broader context. Namely, the CP violation in the standard model is still far below the detection threshold of the EDM experiments today. So it means if we see a non-zero electric dipole moment of the electron, or of the neutron, or of other objects, it's a clear sign of physics beyond the standard model. And it would be a clear sign of CP violation beyond the standard model. And that is one of the ingredients that we need to have the observed baryon asymmetry of the universe. There are different ingredients that need to be fulfilled. A departure from equilibrium, and we need to have baryon number violating processes. And one condition is that we also have extra sources of CP violation, so the violation of the product of charge and parity flips. So these are also low energy precision experiments that help to address one of the most pressing questions. They also help with the strong CP problem. If we look for dark matter, cavities can be useful if the dark matter has a mass range that is compatible with the resonant modes of the cavity. We can use, as we will discuss in detail, atomic and nuclear clocks for searches for dark matter. And if dark matter is connected to the relaxion could also be a candidate that solves several problems. The Higgs mass problem could also be dark matter. There are also scenarios where it could help with a strong CP problem. So in that case, this box extends here. I mentioned atom interferometers. They can look for gravitational waves that might lie in a different frequency range than those emitted from electric phase transitions, but nevertheless the interferometers, atom interferometers and photon interferometers are very useful for such questions. If the hierarchy problem is solved by something like the relaxion, really atomic and nuclear clocks are useful. Neutrino masses could be tested by levitated sensors, so very small, for example, spheres, whose micro-levitation one can test, which is sensitive to neutrino masses. And atom interferometers are also particularly sensitive to the question of dark energy. That was almost 3/4 of this pie that we looked at in the beginning, but we didn't discuss much more here. Okay, so that tells us that it is really reasonable to try to use quantum sensors, and there are many of them, there's not the one quantum sensor, to look for solutions to relevant questions that keep particle physicists and cosmologists busy. Yes, please.
Sorry, before we kind of get into the quantum sensing part, I have a question regarding the previous slides.
Yes, please.
You have been mentioning every time, like, okay, there's this problem, you say, okay, maybe we can make a new particle out of this, or we can do this, make a field and adjust. How does that, for instance, affect the other parts of the theory? Because that would affect,
Good point.
if you're looking at specifically this field, could that then corrupt or disturb other parts, or is this really being seen as like a whole, or not even?
Yeah, that's very relevant. For example, if we say we introduce an axion to solve the strong CP problem and to have a dark matter candidate, would it influence electroweak precision measurements? For example, would it disturb the relations between the W mass, top mass, Higgs mass, which have been measured precisely? Then one has to see how does it couple to these particles and how small is the interaction that has been constrained so far. So these tests have to be done, and they are done. So one typically then does global fits to fit to all available data to see if the introduction of a new particle would disturb our previous measurements. And often it's the case that if we introduce a super light new particle, it doesn't disturb the measurements done at the LHC. But if it's in the mass range relevant to colliders, it could disturb it, and we could learn a constraint on it. It could help to shrink down the parameter space where new experiments should look for it. So there's a fruitful interplay of the different frontiers. Cosmology also plays a big role because, as I mentioned before, if we introduce a new particle, it could contribute to the loss of energy from stars. It could change the evolution of the universe before or after neutrino decoupling, or the different processes of Big Bang nucleosynthesis. All this has to be checked and is checked. Or is still like up to be checked for cases where it hasn't been done. But yeah, exactly. So it relates to this question, like if we extend the standard model, we have to be sure that the standard model remains as a limit of going to the energies tested so far. Okay, so now we go to the sensing. And in this week, you have various lectures about the more technical aspects of quantum technologies, the application to quantum computing, quantum communication, and the, how to trap ions that you can use to build qubits, also to build quantum sensors. And now in this part, so my first part was to clarify for you why we actually want to look for new signals. And now in the second part, we want to see how to look for them. And here among the vast possibilities how to look for the new signals, we focus on quantum sensors. And there we also can't cover all. So I focus a bit on the atomic clocks and also the nuclear clock, which is a very recent development. But before we do this, let's collect what qualifies as a quantum sensor. Who is already fully aware of quantum sensors, or maybe somebody of you works on quantum sensors? Not so much. Who works on maybe quantum computing? Somebody, yeah. Which sensors do you work on? Or you're familiar with?
No. You said quantum computing.
You work on quantum computing? And you? On?
Well, yeah, atomic clocks.
Atomic clocks, cool. Which one?
No, it's pretty much, it's a very similar topic, but they're being built right now. It's like atomic and highly charged ion clocks.
Cool. I will also mention highly charged ion clocks. Yeah, so then maybe it's a bit complementary to your experience, so I'm happy to maybe contribute something that was unclear so far. Yeah, so quantum sensors are now also in particle physics and beyond used as a buzzword to say something cool. If you put quantum sensor and beyond the standard model in an abstract of a paper, of a grant application, it sounds cool, but we should know what it is and how to make use of really of the quantum properties. So one can break it down to some bread and butter physics to say what a quantum sensor is. What we need is to have discrete resolvable energy levels. We can start with a two-level system. So we want to know what is the lower lying state, can be the ground state, and the higher lying state, separated by a certain energy gap. To find out if there was a transition between the two levels, we need to be able to initialize the quantum system in a known state and also read it out to be sure about the initial state. Then we want to be able to coherently manipulate it. Bless you. And the system should be susceptible to interactions with an external field, for example, a magnetic field or an electric field that would introduce an energy shift of at least one of the levels, or would induce, if the energy is large enough, a transition between the two levels. So that's still very broad, and a lot of sensors can fall into this category. So atoms fit perfectly into this picture of discrete energy levels that you can excite. Ions have particular properties that you can trap them well, and you can also strip them of many electrons to have a reduced system of highly charged ions with some quantities that could be favorable for quantum sensors. Rydberg states are states of atoms where the valence electron is in a very high N and high L state, and therefore far away from the nucleus and less affected by nuclear uncertainties. Also, Rydberg states are often stable and therefore favorable to do measurements. But apart from atoms and ions, also superconducting circuits are used for quantum sensors, as well as cavities. Then clocks connect well to also the atoms and ions, and interferometers, both of photons but also of matter waves, such as atomic clocks, where clouds of atoms are excited or travel in an excited or in the ground state. Okay, so these are basically these properties of having discrete energy levels, finding out if something is resonant and being able to manipulate them. That already refers to some quantum world if we have here this discrete energy gap. However, if we just use this definition, we don't necessarily make use of manipulations with quantum technologies. But they can be applied on top in order to enhance the sensitivity of these sensors. And I'm sure in the rest of the week you will also hear more about entanglement and squeezing. So if one entangles, for example, several isotopes before a measurement, that can reduce the uncertainty, as well as squeezing of states such that you reduce the uncertainty in one variable while increasing it in another variable. And that can help to reduce the overall uncertainty in the variable you want to measure. So there are the possibilities to really work with the quantum technologies to enhance the initial sensitivity of such sensors to modifications of dark matter and of gravitational waves or other perturbations of space-time. So such sensors are really well suited for searches for light dark matter or light new physics. So we call it new physics if it's beyond the standard model. Also for gravitational waves, in particular high frequency gravitational waves. And also sometimes people forget that these systems, these quantum technologies can also be useful for high energy physics detectors really implemented at the colliders. Now we look at the advantages of using clocks as quantum sensors. This Nobel laureate, Shavlov, was quoted as saying, never measure anything but frequency, because this is what you can measure most precisely. It's not so surprising that he said it, because he was one of the developers of the laser. So the goal is, if you turn any measurement into a frequency measurement, it's is promising to reach a frequency precision that could be favorable as a tool for particle physics searches. So how can we use atomic clocks as quantum sensors? So here we refer again to this two-level system in atoms, and then if you want to build a clock, you tune your laser to this energy gap that corresponds to this frequency. And initially, atomic clocks were built as microwave clocks. So there, the oscillations of the laser were slow enough to be counted. Now with optical atomic clocks, the frequencies are so high that the counting becomes more complicated, and the invention of the frequency comb really made it possible to use atomic clocks for precision measurements. And then what one does is you scan the laser frequency and you see how often you excite the transition, which fraction of the time the system is in the excited or in the low-lying state. And by changing the incoming frequency, you can scan a resonance and count, you transform it into a counting experiment, how often you excited this transition. And then you're interested in the resolution of this width to find out how narrow the transition is. So traditionally, atomic clocks are also used at highest precision to transform this energy gap into a frequency, into a time measurement, to define the second, and to use it for GPS. But as particle physicists, we are very impressed by the precision of reaching 10 to the minus 18 and less, such that we also want to use them for particle physics, dark matter, and the gravitational wave searches. So here you see the development over time. The development of building atomic clocks started with microwave clocks at the precision of the uncertainty on a frequency divided by the frequency of 10 to the minus 13. That already sounds very good in the ears of a particle physicist, where we consider percent already as good if it's measured at colliders. And they evolved and got better over time. When the first optical atomic clocks were built, their precision was lower than the microwave clocks at that time, but the slope of the development was faster. So at a certain point in time, the optical atomic clocks became more precise than the microwave clocks. And now 10 to the minus 18 is a relative precision. Yes?
Just out of curiosity, do you happen to know, in the gap between 1980 and 1990, were there no microwave clocks developed, or did the figure makers just not find it?
Very good question. This is from some review article, and this plot is often taken. I haven't never checked if there was anything in between, but I guess if there had been, I would have put it. But it's weird that it took so long for the next one. I don't know, honestly. Yeah, maybe somebody else knows.
Optical clocks made out of two-level systems, right?
Yes, they are also made of two-level systems, and optical means, in this case, that the gap between these two levels corresponds to a frequency in the optical spectrum.
So I think it happens when they started to understand how to have a two-level system inside. So it takes a while in order to build a two-level system and use it. Maybe.
But yeah, the question was also here between the two microwave clocks. Yeah. Okay. Yeah. So, how can we make use of such a phenomenal precision for tests of fundamental physics? So here we see again, maybe here this picture now also doesn't show anything in the 80s. Here we see examples of which systems achieved these more recent high precision measurements. So it started with cesium clocks in the microwave era, and now the optical clocks, they use different elements like strontium, ytterbium, but also calcium and aluminum, both in neutral atoms and in singly charged or highly charged ions. Here we also see some interesting threshold that below the level of 10 to the minus 16 precision, there is no realization of the standard unit of Hertz based on the hyperfine level splitting of cesium anymore. Also, relatively recently, the definition of the second was adjusted. So there were records already in 2019 to be slightly below the 10 to the minus 18 threshold with an aluminum clock. But now there are even frequency measurements below this. Maybe it's a little bit unfair comparison to look at this strontium lattice clock that used 100,000 atoms. and reached a precision below the 10 to the minus 20 level. So we see the development is very fast, but so that made it to the title page of Nature. And what the group of Junier in Gila and Boulder did there was to have a separation of two atomic clouds, sample A and B, separated on a millimeter scale, and they measured a gravity gradient on a millimeter scale. So that's already an application of such a phenomenal precision. But it's not a single clock, it's like a sample of two systems. And there is no obvious showstopper inside, so we can expect the precision of the atomic clocks, optical atomic clocks, to become better, even better in the future.
I didn't understand. How do you measure gravity gradients with clocks, or like optical clocks? Like, how does gravity play a role there that you can measure it?
So it affects the metric given on the potential height of these two samples separated on the millimeter scale. These were like also more common applications of clock measurements to test gravity, also in clock networks. But here it was the first time it was done on such a small separation.
So like gravity separated the mirrors a little, and they detected that?
Which mirrors do you mean?
I don't know. Like,
so.
How did gravity play a role such that it affected the optical system such that we measured it?
The gravitational constant, right? Or like gravimeters?
Yes.
I think it's like you trap some atoms, or so like interferometry, and then you release the atoms to fall, and you measure how they fall, and you apply some pulses in between, right?
Yeah, that's for large-scale atom interferometers. That's still a different type of experiment. They explicitly test gravity and dark energy and gravitational waves in the free fall experiment. As far as I know, this strontium experiment in the strontium lattice clock, that was not in fall. It was like trapped in the lattice. So, but it was two samples at two different heights. Yes?
So, but again, if you want to sample gravity using atomic clocks, and you're able to measure time very precisely, shouldn't you also be able to measure position very precisely? In order to be able to do that?
Yeah, so atomic clocks are also used to measure local Lorentz invariance violations. So to measure violations of the homogeneity and isotropy of space-time. That's now a different example. We have to come back to this. Maybe I also have to think more precisely about your question. So that's also an effect. If it relates to your question, so one can measure a phase shift of the clocks, for example, when measuring transitions involving differently oriented orbitals, for example, of an F state of ytterbium. It was measured to the variation of a relative phase of clocks during a sidereal day of the Earth rotation, and because then the different orbitals were differently aligned with a rotation axis, one could use this to determine deviations from isotropy in space-time. So that would correspond to a violation of local Lorentz invariance, and these were always already in early times applications of clock tests. They could also be caused by new dark matter particles, but one can also describe them just as coefficients of changing the metric in a way that violates Lorentz invariance. So the key is often to do differential measurements, to measure at different points in time, or to measure in a network of clocks at different positions, and cancel out some systematic effects and see how a signal changes. And then if you don't see a variation, you can put a bound on such violating, like as Lorentz violating terms. Maybe I have some backup slide on this, or I can tell you later on. And yeah, so to spell out more like what it means to have a 10 to minus 18 precision, we need to compare clock ratios to cancel out, to have a common standard. And for example, the aluminum clock with a 10 to minus 18 precision was referenced to an ytterbium clock. Both measured very precisely, and having a deviation of 10 to minus 18 is equivalent to having a 1 second deviation in 13 billion years, or to measure the distance of the Earth to the Sun at the precision of a fraction, of a 1,000th fraction of a diameter of a hair. So it's, for particle physicists, quite unimaginable to be so small. So how can we use it? First, maybe we want to see what are key figures that determine which atomic clock is usable or less usable, not only for new physics searches, but also in the big endeavor of building very precise atomic clocks of different systems. That's already an achievement by itself and incredibly complicated and depends a lot on the system. There one wants to know well how the frequency develops in time, how accurate it is, so how much it deviates from the true value, and how stable it is in time. So these are two key parameters that influence how precise a clock can work and how well we can use it for dark matter searches. On the one hand, for the accuracy, shifts are important. Shifts that come, for example, from relativistic effects, relativistic Doppler shifts, or also from field shifts or interactions of the clock with external fields. At the end, if many sources are already controlled, micromotion is still a topic. Another topic is how stable the clock is, how it develops over time. That's the stability. That's characterized by the Allen deviation, that where this uncertainty on the stability scales with the duration tau, 1 over square root of tau. Then noise is an important topic, how much noise is there in the system and how does it scale when we repeat an experiment n times. There, on the one hand, we are limited by the standard quantum limit, where the uncertainty only falls with 1 over square root of n, but by quantum technologies, especially by squeezing, by entanglement, one can reach 1 over n scaling, and how coherent the signals remain. Okay, so now we switch to a bit to how new physics would influence the transitions of the clocks. Now we can imagine that we have a light new scalar that couples two electrons and neutrons in the atomic spectrum in the atom. And if we have a system without a new scalar, we have the nucleus, we have the electron levels, a two-level system here, where the energy gap corresponds to a photon of a certain frequency, and the presence of a new particle could disturb this frequency, could shift it by some small amount. And the question is, can this change of the rate of clocks be detected, or would it be too tiny? Would it be overshadowed by the overall uncertainties? Now we can model this new particle that couples to the nucleus and the electrons by a so-called Yukawa potential. So its interaction range is determined by the mass of this new particle, and the interaction strength is dependent on the coupling to electrons and neutrons. However, the changes are small, and the changes of the energy levels are small. And if it's a system with many electrons, then the theory calculations are far less precise than the experimental measurements. So we cannot directly translate an experimental precision of 10 to minus 18 into a 10 to minus 18 precision on finding out about the interaction, because the nuclear and the theory uncertainties are larger than that. On the other hand, if it's a system with few electrons, then the theory calculations can become as precise as the experimental ones, and one can directly compare if there's a mismatch between the experimental frequency measurement and the theory expectation from the standard model, plus minus their respective uncertainties. And in this gap, plus minus uncertainties could be the room for new physics. We could then say new physics cannot be larger than this difference. However, if we work with with many electron systems, then we need to find out a way to cancel the leading uncertainties. And here I want to show you one example from some collaborative work involving atomic experimentalists and theorists and particle theorists. I was also involved in this over now several years. And there we propose to measure two transitions in at least several isotope pairs very precisely, such that the leading uncertainties cancel out. So if we compare the same transition I in two different isotopes A and A prime, we call their difference an isotope shift. That can at leading order be described as the mass shift resulting from the relativistic effects of adding an additional neutron to the nucleus. And in the second part, it's a field shift by changing, or it's also called volume shift. Even if we only add neutrons, we don't change the nuclear charge, but we change the nuclear charge distribution. And each of these terms is factorized into an electronic part and a nuclear part. That's possible to factorize, at least approximately, because these two effects take place at very different length scales. The electronic parts at much larger length scales than the nuclear ones. However, if we want to compare this, if we want to do a theory calculation of the electronic coefficients and measure the reduced masses, where we are faced with an unknown or only poorly known nuclear charge radii, so that we cannot directly compare experimental theory, but we can measure a second transition and replace these unknowns, the unknown charge distributions, by the second frequency, and that helps to express frequency 2 in terms of frequency 1 times ratios of these electronic coefficients. So at leading order, the expectation is that transition 2 will depend linearly on transition 1. Yes?
Can you repeat what you mean with the second transition?
So if we say we measure transition I equals 1, so that could be between level 1 and level 2, any level. And transition 2 could be between level 1 and 3. So one could be a S2P transition and the other a D2P transition, for example. So two different transitions between the electrons of the same atom or ion.
Okay, so in this case it's not useful to use a two-level system.
No, there we would need a three-level system, at least, yes. That's right. And then we can write this, copy this equation for the second transition and replace the unknown. And that was already an expectation from the 60s, that one would expect linear relations in the so-called king plot of plotting one transition against another. So that's already nuclear physics from and atomic physics from the 60s. How can we use this for particle physics? We could imagine that if we have new physics that depends on this coupling of the new particle to electrons and neutrons, that could change this linearity relation. And here's some older data from 2015 where we see in calcium plus transitions the king plot looks linear within the uncertainties. So one can use this to put a first bound on new physics if we check if 3 points are within the uncertainties on a straight line. So this is one example of transforming clock measurements into a test of new physics, because we can say if there was new physics with couplings larger than a certain amount, it would cause deviations from linearity larger than the uncertainties. So if it turns out to be linear, we can put a bound. And that was the story how it developed. First, from this data from 2015, we applied our method and got a first bound on the mass of a particle and in the interaction strength. Maybe you remember one of these first plots of the lecture where I showed you this parameter space of unknown mass and unknown coupling, where we say this upper left corner is the one that is easy to test. If the interaction strength is relatively large, we could easily see such a process. If we don't see it, we can exclude the region. And indeed, this area, this triangle, was already excluded by a competing measurement. Namely, that we imagine if we have a new light scalar that couples to electrons, we can constrain its coupling to the electron by a precise measurement of the G-2, the magnetic moment of the electron. That agrees well with the standard model up to a very small deviation, and that allows to put a bound on the electron coupling. And then this comes from neutron scattering, so a complementary experiment. So this parameter space that we want to constrain with the atomic clocks is not completely empty, but there are already pre-existing bounds. And if we want to be useful, we should better find a way of constraining the unknown parameter space where the dark matter, where the dark bosons could still live. So let's think again about what we actually search for. We search for scalar bosons, spin zero particles, phi, that could serve as a mediator between the dark sector and the visible sector in a mass range given in electron volts here. And we only require them to couple to electrons and neutrons. They could also couple to something else, but in this experiment, we are not sensitive to it because we compare isotope shifts. They have the same proton number, so if we take differences, the coupling to proton cancels out. So that's why we say we only look for the coupling to electrons and neutrons. But then we see, okay, this parameter space is already constrained. However, this is not the last word of the atomic clocks. A few years later, other transitions involving the d-fine splitting of calcium plus ions was measured in Aarhus in Denmark, and this bound already within 2 years, improved the previous bound by a factor of 30. That usually doesn't happen in collider experiments. Yes.
What is this peak coming from?
It is what? The peak. Yes, good question. So in this bound, we compare which nonlinearity is found in the data to compare to what we expect from the theory if the new particle couples to neutrons and electrons. And there we get electronic new physics coefficients. And in the bound, when we calculate, we get a difference of 2 terms in the denominator. So if this denominator accidentally gets 0, we get these spikes. So that means at these masses of the spike, we basically don't have sensitivity. There could be a new boson, but we wouldn't find it with this combination of transitions. So therefore, it's important to compare different transitions, not only 2, but to have systems with more transitions, because they will have their losses of sensitivity at different masses. And if we do several measurements, we can cover a broader parameter range.
So you might expect different transitions and other peaks?
Yeah, different transitions have their peaks at other positions. Yes.
So how the difference between the peaks will help us to detect these new particles?
These differences don't tell us about the...
No, I mean, you said if we have different transitions in the same one, we should expect different peaks.
Yes.
Alongside we are going up. So the difference between the peaks for the information we can get.
They are a prediction from the theory where the peak is. But what I meant is here in this area of the peak, we are blind to the new particle. But if we have another pair of 2 transitions, maybe with similar sensitivity, but it has its peak here and has a good sensitivity here, we can bridge the gap where we don't see, where we would miss the particle if it was there. Here we see the peak at different locations because this was an S2 peak compared to a D2 peak transition, and this one was involved a D3 half to D5 half transition plus combined with another transition. So that's why they have their peaks at other locations. So, but still, even after a factor of 30 improvement, it wasn't better than existing bounds. We made estimates that future experiments of reaching higher precision, not only clocks with 20 hertz or 100 kilohertz transition, but sub-hertz transitions of other elements, calcium, barium, ytterbium, could test new parameter space if the King plots remain linear. So that motivated also experimentalists to further develop other clocks. In the meantime, we also interpreted these bounds in other models, for example, with the dark photon that I described earlier as mixing with a visible photon, or having a new gauge symmetry that is a U1 symmetry of baryon minus lepton number. Okay, but then what happened next was that it was not so easy to just continue setting bounds, because then the story developed that suddenly in 2020, a team from MIT measured isotope shifts of ytterbium more precisely than ever before and found this nonlinearity that I showed you as an advertisement on one of the first slides of deviations from the standard model expectations. So that was already quite significant. And journalists approached the ytterbium team in that year that measured the nonlinearity. In the same year, a calcium team in Aarhus measured linearity in calcium. So the question was, are there dark bosons out there that only couple to ytterbium? What is the story with calcium? So it's not per se a contradiction. It can be that the effects, the nonlinearity effects in ytterbium are bigger than in calcium. And in particular, ytterbium is a bigger element with a bigger nucleus. So this started the era of not ignoring nuclear physics anymore, because this relation of linearity that we saw in the beginning only holds at leading order. So if we ignore higher order effects, so if we do a perturbative expansion of the effects, if we ignore higher order effects of the standard model, then the linearity holds. But there could be nonlinearity on the one hand from beyond the standard model effects, or also from higher order standard model effects, such as the deformation of the nucleus, or higher powers of the charge radius, or the fourth moment of the charge radius distribution. So we had to tell the journalists that it's too early to claim dark bosons. It could as well be nuclear physics, and more research needed to go into this. And the strategy then changes into, if we find nonlinearity, we should check what is the standard model effect, and if we can subtract it, constrain the residual nonlinearity. So this year, also the team by Tanja Milchstäubler at PTB measured the ytterbium shifts, isotope shifts, even more precisely. And the good situation is that in ytterbium, it's not just a two-level system, but because it's a relatively complicated system with a big nucleus and many electrons, there are different transitions available. This S to D5 half, S to D3 half, whose difference is the defined splitting, then also involving an F state that was measured both at MIT and at PTB, then also another S to P and S to D transition that were measured at high precision. So that allows us to test different hypotheses. I always said we cannot verify, but we can check compatibility of the data with different hypotheses to see what in the deformation of the King plot, which shape the linearity has if we have 4 points. So in ytterbium we even have 5 isotopes, so that form 4 isotope pairs. If it's nonlinear, it could form a zigzag shape or a C shape, like a happy or sad smiley shape. This shape tells us about compatibility with different assumptions if this nonlinearity comes from higher powers of the charge distribution. Nuclear theorists even calculated ab initio some higher moments of the charge distribution that seem to explain a majority of the nonlinearity, but we also see large uncertainties. So even the new boson hypothesis, this dashed dotted line, still lies within the range of possibilities. So we cannot exclude that there is a dark boson, but it's quite likely that the dark boson is not the only explanation for seeing such a nonlinearity.
What is the lambda minus?
So this I didn't explain, sorry. This is the characterizing how much the nonlinearity is more a zigzag shape or more. So if you have a line and 4 points, you can have the possibility that there's 1 point below, 2 points above the line, and 1 point below the fitted line. Or you could have below, above, that would be a zigzag shape. If it was 1 below and then 3 above, it would influence the fit such that the line would be tilted differently, or the other way around. So there are these 2 characteristic deviations from linearity. And the lambda plus, lambda minus measure this shape. So it's about learning more from the data. And then still taking now this new nuclear physics knowledge into account. So it's really an example where it's not enough to do atomic and particle physics. Now we need to do atomic, nuclear, and particle physics in order to understand the data best by subtracting or by taking into account an additional source of nonlinearity, namely this nuclear physics effect. We could still set a bound on new physics, and here you see the development of new physics bounds still in this plane of the coupling to electrons and neutrons and the mass, and now again on the log plot. And we see that this new ytterbium measurement combined with the older ytterbium measurements improved the bound, but still is not better than this G-2. In the meantime, also the G-2 improved. So the question is, how can we move on? Maybe, so ytterbium is very promising because there are so many isotopes and so many transitions.
But just one question.
Yes?
See that the Ca and the ytterbium have the same peak. Why? But they have different nucleus.
Yes, very good question, very good observation. We were also puzzled by this. And we cannot explain it from first principles, but numerically they coincide to have a similar place. They are not exactly equal. They are a little bit shifted, but not by much.
Why?
Yeah, why? So yeah, you could also ask why maybe is there symmetry between them. So far it was more, I don't see a symmetry, but sometimes, I mean, all this was about the guiding principle of symmetries. We don't have an explanation for this. Like, it's also not an easy calculation, but it's done with a numerical code that runs non-perturbatively to evaluate the impact if we add a new physics potential to the Hamiltonian. How will it impact the solutions of the Schrödinger equation? So what wave functions will we get out?
They account for a transition, right? It's
Yes.
that in each of the system, they have the same transition. Upon taking this transition, does it mean that there's a different transitions and there are in the other material different transitions that coincide?
It's a cancellation of two terms of and here we take a generalized king plot where we plug in 3 transitions into one bound. So there it's a determinant of terms where there are several differences. So it's there are several terms that add up and come out similar. Yeah. So then the question is, how can one move on? So ytterbium was already very powerful with 5 transitions and 4 isotope pairs. What would be complementary? And you already mentioned you work on highly charged ion clocks. So highly charged ions are indeed a very powerful tool to enhance some effects and suppress some unwanted effects. So in the next slides, I will show you some complementary results of testing new physics now based on calcium transitions again. We had them in the beginning of the story, but this time combining singly charged calcium clocks with highly charged calcium clocks. And so what happens is, so here you can imagine a nucleus with an electronic cloud of a neutral atom or an ion. If you strip away many electrons, you end up with a, if you take away all but one, you have a hydrogen-like ion, where just 1 valence electron remains. If you leave a few, but much less than the full number of electrons, it's a highly charged ion, where the remaining electrons of the core are much more closely bound to the nucleus. So this distance between nucleus and electrons becomes smaller, and also the intuition of the scale ratios is a bit different. An advantage is if you take away several electrons, you have less combinatorics of inter-electron interactions. So you reduce the calculational difficulty of the multi-body electron effects. On the other hand, the QED effects grow with the charge to the 4, and unwanted effects that impact the accuracy of the clock, namely the shifts that we had on one of the slides, like the Stark shift is reduced with a Z, so the charge to the -6. So highly charged ions are particularly promising to reach high accuracy in traps. So they are also easily trapped. Not so easily, but that's not true. It's a very complicated procedure to produce the highly charged ions and to trap them, but then they promise high accuracy. Also, the electrons are more closely bound, so what we could ask the question, maybe they will be more sensitive to test shorter interaction ranges between the electron and the neutrons. So the highly charged ion clocks, they are also very sensitive to time variation of fundamental constants. So we will come to this. They can therefore be used to test ultralight dark matter. Very high precision has been reached in the challenging highly charged ion clocks, almost competitive with singly charged ion clocks, and they are ready for even isotope shift measurements, and that's what we did. So at PTB, so that's one of my affiliations, but there's amazing to learn from the experimental colleagues who actually built the clocks in a big clock hall. The team of P. Schmidt built first this highly charged aluminum clock, and then the highly charged calcium clock. It was calcium 14 plus, and achieved measurements at the sub-Hertz level. And we combined those with measurements, new measurements done at Zurich by the team of Diana Craig to measure calcium in singly charged calcium, a complementary transition. So for these new physics tests, it's very useful to have quite complementary transitions. If they are very similar, like S2D3½ and S2D5½, their sensitivity to new physics is reduced. But if you find characteristically different transitions, like in calcium 14 plus versus calcium plus, they bring an enhanced sensitivity to new physics. And also we combined it with a defined splitting transition measured before. And here one can see the earlier bounds, also the ytterbium from MIT in 2022, then the ytterbium including the new PTB data from this year, and in blue. And now in green and red, we have two methods of extracting a bound from calcium and calcium 14 plus, and even an update that I haven't included here yet, to subtract a theory calculation for the second order mass shift, which is relevant in calcium. That's more relevant than the field shift corrections. So also here, until now, in calcium, everything was simple, everything was linear. This is the first time now, and it will come out hopefully next month as a paper, that even in calcium, one can see nuclear effects. It means it's a big credit to the experimentalists, because now the atomic precision is so big that one can see nuclear effects via atomic measurements, and they pose a challenge for particle physics interpretations. But theory colleagues at PTB have now calculated higher order corrections to the mass shift of calcium that we were able to subtract before doing this database analysis, and can now set a bound that is better than the ytterbium bound. So it's still improving, and we get very close to testing new parameter space, but the way forward will still be to measure more elements, also some with more isotopes, but it's limited how many isotopes, how many stable isotopes there are per element. And now is the era that we need more nuclear theory input to make more progress on particle physics interpretations. Okay, now I talked about how to constrain like this intermediate mass range of new scalars. So it's not considered ultralight. So here we start with EV or 10 EV and go to MeV. We stop where the inverse mass of the new mediator corresponds to the nuclear size, because there the new physics effects would become indistinguishable from the nuclear effects, because the Yukawa potential of the new physics gets closer and closer to the delta function, and the nuclear potential, seen from the point of view of an electron, is basically a delta function. So there we can't say, we also see the bounds get very weak. So this is a relatively, it's still below a GeV scale, but not ultralight dark matter. It would be intermediate mass scale dark bosons. That's one range one can look at, and here I presented to you the option of doing isotope shifts. In the next step, we want to look at the ultralight mass range, where other effects play a role. Yes, please.
I'm still having a difficulty understanding this plot.
Yeah, it's a bit busy, yes, sorry.
But maybe give us an insight of how, what you would expect from this plot if you say, let's say, find what you want. What you're looking for? What would you expect to see?
Yeah, so we keep expecting to see nuclear effects because the atomic measurements are so precise. So measuring transitions between electrons are so precise that one can see effects of the nuclear deformation on the electron levels. What I would like to see in the future is that nuclear theorists can calculate these effects so precisely that we can take them into account and see if any nonlinearity remains there that could come from new physics. And with that, I would like to move forward to test parameter space that is not yet constrained by a competing experiment. So, but what this plot shows is how fast the precision of the experiments grew, and that we kept improving the bounds, but we see here they come closer to each other, even though the precision increased. We are now not limited by the experimental precision, but we are limited by the nuclear effects that play a role now. That is now a change in the paradigm. Yes?
But also we see that peak vanished.
Yes, it happens at even larger masses that we don't show here anymore because it's in the nuclear range. There is still a peak, but it happens outside this plot range.
Why?
Good question. So there's different physics involved now in this scale of highly charged ions. So the new physics sensitivity, or how much the electronic levels react to a new boson coupling to the electrons and neutrons, is then different.
We get information about the peaks that are before that vanishes or no?
You mean, can we see it directly from the...
Yeah, because you said the peak shift, that means this is now a sensitive area.
Yeah, so it
It's
means...
not sensitive
Yes,
before.
yes, exactly. So we see here, the ytterbium lost sensitivity here, but with a highly charged calcium, we can cover this range. In ytterbium, we would have said we have a blind eye on any dark bosons that sit in this mass range. If they exist, we wouldn't find them. But with adding calcium, we see how important the complementarity is, that with calcium, we can cover this range.
And also one more question, why when you go up in the mass, this Q is related to effects that are not known, or there's a limitation?
So if we go up in the mass, you mean why do we lose sensitivity? This is because the new physics potential resembles more and more the nuclear potential. So the new physics coefficients go more and more towards the field shift coefficients, which arise from the nuclear charge distribution. And because of this alignment, we lose sensitivity. So it tells us there other methods will be better to look for new physics. We don't claim this is a method that can find new physics anywhere. Yes?
Kind of also to ask the question, why do you believe that the fifth force has this straight model exactly at around the 100, which is also present on the
Yes. So this is a bound that comes from this yellow is already excluded by astrophysical bounds, namely the cooling of stars that live in globular clusters. And that's a bound that stops roughly at this mass range because of the temperatures that play a role in that process. So that's determined by astrophysics. It has a slope, but on this log plot it looks very straight. But further down it extends to even smaller couplings. This is there it becomes more sensitive to the mass. Why do we nevertheless plot this region? Because this is an astrophysical bound, and we would still like to have an independent laboratory probe of the same hypothesis, which is better under control. On the other hand, this astrophysical bound extends to couplings further down. Even if there was an uncertainty, some bound would remain. So our target area is to find atomic systems, or even then in the future nuclear systems, to look at this white spot of the dark matter or dark boson landscape where not even astrophysics has put a bound. This comes from some Casimir effect, so it's a complementary search for fifth forces. And that extends also further down. That's why that was our motivation to cut the plot here, because once these fifth force bounds, first the Casimir force, and then come the equivalence principle tests of pendulum, they are better than the King plots. The King plots stay constant. Nobody asked why this, but I also haven't explained. They stay constant here because in this range, the interaction range of the new physics interaction already fills the whole atomic volume. So if we go smaller in the mass, the interaction range becomes larger, but we don't test more electrons because we already included all in our interaction volume. So the interaction length is inversely proportional to this mass that determine in the Yukawa and Yukawa potential what is our interaction scale. Okay, I'm checking the clock, speaking about clock bounds. Now it's 5:20. We are supposed to end a bit before 5:30, such that we go on time to the boat. So there was something, I can skip the other things, but there was some development I would really like to tell you about, and that's the nuclear clock. So I will also join you on the boat so we can discuss more unanswered questions there. But the developments of a nuclear clock are in these weeks and months so exciting that the timing of this lecture, I think it would be a pity if I don't mention them. For this, let me quickly motivate why we also interested in superlight dark matter. So I don't want to speak too long about this Lagrangian. I said we described our interactions in a Lagrangian of a new field phi that we had before. Now we don't describe it via its Yukawa potential, but via its interactions with the fermions, gluons, and so on. You don't need to look at every term. It's rather the case if it's very light, it builds coherent waves of oscillations in space-time. So it forms, independent of the space, forms coherent waves in time, and the frequency is determined by the mass. You can imagine it like this. What impact it will have? It will make the fundamental constants oscillate. So if we think alpha, electromagnetic, is constant, in the presence of an oscillating dark matter field that couples electromagnetically, also alpha will fluctuate. And also the fermion masses will fluctuate. Why? So the energy gap between in our two-level system is determined by the electromagnetic interaction. So if alpha fluctuates, also the energy gaps fluctuate, and we can observe this, we can look for it by time variation of frequencies. This is done by clock comparisons of ytterbium clocks here, but we jump over this. How can we choose which system is particularly sensitive? So we want to know how a change in alpha translates into a change in the frequency. And their proportionality factor tells us about the sensitivity. So we want K to be large, such that even a small variation in alpha could result in a measurable frequency variation. The other way around, if we measure super precisely with 10 to the minus 18 precision, the stability of frequencies, and we don't see an oscillation, we can conclude, if this coefficient is large enough, we can conclude that the changes in alpha have to be very small. That means also the amplitude of the dark matter must be very small. So or it means we could exclude this dark matter in this range, or we would also have the chance to detect a signal if there is some variation. So we are interested in finding combinations of frequencies that result in a large K. So here you can see there are better and worse choices of frequencies in strontium, ytterbium, aluminum, and so on. Some are larger than 1, some are small. At the end, we compare 2 frequencies. Highly charged ions reach even tens of a K of like up to 70. And that help to look for this ultralight dark matter. This is now a very busy plot. We jump, or I can only maybe say again, it's a mass. You look at the mass range of sub-EV, super sub-EV, down to 10 to minus 22, or even lower. That's where the wavelengths of the dark matter reaches the size, where the Compton wavelengths reaches the size of the galaxies. And here it's a super interesting physics scenario. So many people put bounds on this. I haven't contributed to this plot, but it's interesting to see what is the range of interest. We want to probe parameters even below this naturalness line, such that we don't introduce a new hierarchy problem. We see that clock comparisons, recent ones here, contribute already to such a sensitivity. And now we see an ominous nuclear clock on this plot that would improve the sensitivity gigantically. So the last minutes I want to dedicate to the development of a nuclear clock. So far we heard about atomic clocks. That means they are transitions between the electron levels. We haven't talked yet about transitions that could occur inside the nucleus. Why? Because most transitions between a ground state and an excited state in the nucleus lie in the MeV range. That's the range you know as physics of, the range of nuclear physics. However, MeV range energy differences correspond to so short wavelengths that they are inaccessible by lasers. So all these advantages of having a good laser to to build a clock are not present here. All apart from 2 nuclear transitions known so far lie in this MeV range. There's one transition of uranium lying here at 100 eV range, but with a lifetime so long that we can't observe this transition. This yellow blob shows where we have our good atomic transitions, so transitions between electrons in the electron shells. And this is the range, the EV up to 10 EV range, where we have lasers. And in this range, there's exactly one transition, and that's between the ground state of thorium-229 and the isomer of thorium. And that's a puzzle. Why is this 10 to the 5? Why is it 5 orders of magnitude lower than the other nuclear transitions? The reason is a rare cancellation of 2 terms that have almost the same size. So normally, the differences between the ground state and an isomer, so an excited nucleostate, are in the MeV scale. But for thorium-229, the Coulomb contributions almost exactly cancels some effects of the strong interaction, so that only a small energy gap between the ground state and the isomer of 8 eV remains. That corresponds to 148 nanometers. That it's not exactly in the what we call optical. It's rather VUV, but it's still in a range borderline to have a good laser. And new lasers had to be developed to operate really well at such a short wavelength of 148 nanometers, but it's still at the order of magnitude of optical transitions. That's why we call it an optical nuclear clock. And that's very exciting for nuclear physicists and anybody building a clock. But why are also particle physicists super interested? You remember this sensitivity factor of connecting a change of a frequency of a change of an of a fundamental parameter to a change of a frequency. It's up to order few for ions, 70 for highly charged ions, and 10 to the 4 for the nuclear clock, because some other effects cancel and the sensitivity is enhanced. This is still an estimated precision calculation, has still to be done, but that's the way forward. There have been 20 years of searches for this transition to laser-excited nucleus. Many things happened on this. Here, I know that lots of things happened, and I didn't put them on this axis because I want to focus on the recent developments. It was last year that at CERN, a new pathway of producing more of the thorium isomer was realized at Isolde via some new chain, so that improved the knowledge of where this transition sits. It was already expected since 2003 that there should be such an 8 EV transition, roughly 8 EV, but the knowledge was too rough in order to point a laser at it. So that improved the precision from percent level to 10 to minus 4, thanks to the developments at CERN. Then the breakthrough happened now in the winter at PTB, where the group of Eckhard Pike realized the first laser excitation of a nucleus. So far, nobody had laser excited the nucleus and seen the transition. That was made possible by their collaboration with the TU Vienna that produced crystals doped with thorium ions in order to have more thorium to at least see some transition. And they did a scan with a broadband VUV laser and found a transition had this frequency with a precision of 7 gigahertz corresponding to a relative precision of 10 to minus 6. So again, another 2 orders of magnitude development, and for the first time one could really resolve the line shape of this thorium transition. So that was a breakthrough. And shortly after, the team at the University of California in Los Angeles, the group of Hudson, improved the precision from 7 gigahertz to 3 gigahertz. And now, very recently, last month, Jun Ye's group at Gila in Boulder in Colorado built a VUV frequency comp. So the recipe that was successful for optical atomic clocks is now also successful in improving the precision for the nuclear transition. It's not yet a clock, so they reached a precision of 300 kilohertz, so a relative precision of 10 to minus 10. It's not yet 10 to minus 18, but the nuclear clock has the potential to even exceed the precision of 10 to the minus 18. And it has this of orders of magnitude enhancement to the sensitivity to new physics. So it is very interesting now to study, even from this broad line shape. It's still limited by the laser line width, but this is the line shape that my colleagues at PTB measured. And with particle physicists, we were now wondering, okay, what if there's oscillating light-dark matter? Could it broaden this line shape even further? If it doesn't, if this is our limit on the broadening of the line shape, how much could there be dark matter? What can we learn from the thorium transition? It's not yet a clock, but the transition. What can we learn now? Yes, please.
Yeah, very short question. The last slide, it said VUV, I think.
Yes.
I missed the definition of that.
That's the vacuum ultraviolet. So it's even shorter wavelengths than what you call ultraviolet. Sorry for not defining it here. I thought that the quantum masters of quantum technologies are better than me in all these wordings. So it's still early. It's not yet a clock, but already from this early measurement, it's published now in PRL, this experimental measurement, we managed to learn a little bit about dark matter. So this is, again, ultralight dark matter. And in interaction strength, how much it couples to the gluons. And with this 7 gigahertz resolution of PTB, we think we can have sensitivity up to there. It's still not competitive with other bounds. But reaching 1 kilohertz, which will be possible even on a short time scale, according to the experimentalists, it will improve the bound gigantically, and ultimately building a thorium nuclear clock, so really having a stable clock with high accuracy, high stability, will constrain parameter space of these dark bosons so deeply in the parameter space that it will, after realizing the clock, will have the potential or will have the sensitivity to test uncovered parameter space. So with this, I think I conclude. I would have otherwise, if I had been faster, but maybe I explained too much, have told you also how to use atomic clocks to look for high-frequency gravitational waves in regions that haven't been tested so much yet, but we can chat about it on the boat. And do you have urgent questions, or should we discuss them on the boat?